So here is something that should bother you a lot more than it probably does. Everything you can see right now, the room around you, your own hands, the light in the room, the glow of whatever is playing this for you. All of it is built out of tiny little things that do not actually obey the rules you think the world runs on. The chair you are sitting on is solid because of a rule that says two of these tiny things are not allowed to be in the same situation at the same time. The sun is shining because of a trick where particles pass through walls they should not be able to pass through. And the very device playing this for you works because somebody figured out about 100 years ago that the world is fuzzy and random and refuses to tell you what it is doing until you actually look. This is the story of how we found that out, told as slowly and as completely as I can possibly tell it. Now, before I go any further, I want to be honest with you about something because it matters. I am not a physicist. I am not a scientist of any kind, really. I never got the degree. I never worked in a lab. And if you put me in a room with an actual quantum theorist, I would mostly just nod and try not to embarrass myself. I am just a guy who likes reading about stuff online late at night when I probably should be doing something more useful, and then I like talking about the stuff I read. That is the whole thing. That is the entire channel. I read up on something that grabbed me. I go down the rabbit hole way further than any normal person should, and then I sit here and yap about it for hours, so you do not have to do the reading yourself. So if you are an expert and you catch me getting a detail slightly wrong, you are probably right, and I would genuinely love to hear about it in the comments. But the goal here was never to be a textbook. The goal was to be the friend who stayed up too late learning about something strange and could not wait to tell you all about it. And one more thing while I have you, and then I promise I will get out of my own way and start the actual story. If you like these long ones, the slow ones, the episodes where I just go through everything, I put them all up over on my Patreon, completely free of ads. No mid-roll breaks, no sponsor reading in the middle of a sentence, nothing that yanks you out right when you are finally getting into it. Just the full thing, start to finish, the way it is meant to be heard. So if that sounds good to you, the link is down in the description, and it genuinely helps me keep making these. All right, that is enough out of me. Let us talk about the strangest thing human beings have ever discovered about the world. So, to understand why any of this was such a shock, you have to go back to the end of the 1800s, to a time when physics felt basically done. And I mean that. There were serious, brilliant people back then who genuinely believed that the big questions had all been answered, and that all the future of science had left to do was measure the numbers a little more precisely. A famous physicist named William Thomson, who later got the title Lord Kelvin, supposedly told a room full of students near the turn of the century that there was nothing new to be discovered in physics anymore, and that all that was left was more and more exact measurement. Now, historians argue about whether he said it in exactly those words, so take the quote with a grain of salt, but the attitude was very real, and a lot of people felt that way. And honestly, you can see why they felt that way, because the physics they had was incredibly good. They had Isaac Newton, who had handed them a set of rules way back in the 1600s that told you how absolutely everything moved. If you knew where a thing was, and you knew how fast it was going, and you knew the forces pushing on it, then Newton's rules would tell you exactly where that thing would be at any moment in the future, forever. You could point a telescope at a planet and predict where it would sit 1,000 years from now. You could fire a cannonball and know where it would land before it left the barrel. The whole universe, as far as anyone could tell, was a giant clockwork machine, and Newton had handed us the instruction manual. Then, in the 1800s, a Scottish man named James Clerk Maxwell came along and did something almost as impressive, because he took electricity and magnetism, which everybody had thought were two separate things, and he showed with a handful of equations that they were really two sides of the same coin. And buried inside those equations was a stunning surprise, which was that light itself, ordinary, everyday light, was nothing more than a wave rippling through the electric and magnetic fields, traveling at one specific speed. The speed we now know is about 300,000 kilometers every single second. So by the end of the 1800s, you had Newton explaining all the big chunky stuff, the planets and the cannonballs and the falling apples, and you had Maxwell explaining the light and the electricity. And between the two of them, it really did look like the whole picture was painted. And all that was left was to clean up the edges. But there were a couple of edges that would not clean up. There were these two little nagging problems, these two tiny experiments that the beautiful clockwork picture could not quite explain, and they were so small that most people barely paid them any attention. Lord Kelvin himself, in a lecture around 1900, called them two clouds hanging over the otherwise clear sky of physics. He thought they were minor. He thought somebody would clear them up in a few years, and the sky would be blue again. He could not have been more wrong, because those two little clouds were about to grow into a storm that tore the entire clockwork universe apart. And one of those clouds is exactly where our story really begins. So the first cloud, the one that matters most for us, came from something incredibly ordinary, which was the question of why hot things glow. And I want you to really sit with how normal this question is, because that is part of what makes the answer so strange. You already know that hot things glow. If you have ever watched a metal poker sit in a fire, you have seen it. As the metal gets warmer, it first starts to glow a dull red, and then as it gets even hotter, the red brightens up, and if you could keep heating it, the glow would shift toward orange, and then toward a yellowish white, and eventually toward a bluish white, the way the very hottest stars look. So the color of the glow tells you the temperature. This is not magic, it is the everyday behavior of anything warm. And physicists in the 1800s wanted to write down the exact rule for it, the rule that connects the temperature of an object to the colors of light it gives off. To study this cleanly, they came up with an idea called a black body, which sounds fancier than it is. A black body is just an object that soaks up every bit of light that hits it and reflects none of it back, which means any light coming out of it is light it made itself, purely from being warm, with nothing bouncing off to confuse the measurement. In the lab, the closest thing they could build was a hollow box, like a little oven, with a tiny pinhole in one side, and they would heat the box up and measure the light streaming out of that pinhole. And the question was simple to ask and brutally hard to answer. For a given temperature, how much light comes out at each color? How much red? How much orange? How much violet? How much of the invisible colors beyond? Now, here is where the trouble started, because the best physics of the day, the beautiful Newton and Maxwell physics that everybody trusted, made a prediction about this, and the prediction was insane. The thinking went like this: light is a wave, and inside that hot box, the light waves can rattle around in a whole range of sizes. The long lazy waves, the reddish ones, there are only so many ways they can fit inside the box. But the short tight waves, the violet ones, and the ones beyond violet, there are way more ways for those to fit. And the math said each one of those tiny waves should be carrying its own equal share of the energy. And because there is basically no limit to how short a wave can get, that meant there were endless numbers of these tiny short waves, each demanding its own slice of energy. Add it all up, and the answer you get is that a warm object should be blasting out an infinite amount of energy, almost all of it at the violet end and beyond, in the ultraviolet. This was, obviously, completely embarrassingly wrong. If it were true, every warm object in the universe would be a death ray. Opening your oven door to check on dinner would flood your kitchen with a lethal blast of ultraviolet, and you would be incinerated on the spot. Sitting near a campfire would be the last thing you ever did. Your own body, which is warm, would be glowing with deadly radiation right now. None of that happens, obviously, and yet the math of the best physics in the world insisted that it should. This disaster got a name a little later on, and the name was the ultraviolet catastrophe, which I think is one of the better names physics has ever produced, because for once, the dramatic word actually fits. The whole clockwork picture of the universe predicted that you would be killed by your own toaster. So that was the cloud. The experiments showed something perfectly sensible, where the light came out, climbed to a peak at a certain color depending on the temperature, and then tailed off and dropped back down toward nothing in the ultraviolet. But the theory said the curve should shoot up to infinity and never come back. The shape that nature actually produced and the shape that the math demanded did not match at all, and nobody could figure out why. A few people had managed to write down formulas that fit one half of the curve or the other, but nobody had a single rule that fit the whole thing. And more importantly, nobody had any idea why nature behaved the sensible way instead of the catastrophic way the equations insisted on. The man who finally cracked it was a German physicist named Max Planck. And he's one of my favorite characters in this whole story, because he absolutely did not want to be the one to break physics. Planck was conservative by nature, and I do not mean that in a political way. I mean that he loved the old rules, he trusted them, and he had spent his whole career believing in the orderly clockwork picture of the world. Historians have called him a reluctant revolutionary, and that is exactly right, because the thing he was about to do horrified him, and he spent years afterward trying to undo it. He was born back in 1858. He came from a family of academics and lawyers and church people, and he was the kind of careful, proper, serious scientist who wanted nothing more than to firm up the foundations that already existed, not to blow them up. So Planck went after the hot, glowing box problem, and at first he was just trying to find a formula that matched the measurements. And in the autumn of 1900, he found one. He came up with an equation that fit the experimental curve perfectly, across every color, the whole shape, with no catastrophe at the violet end. That part was a triumph all on its own. But Planck was not satisfied with just having a formula that worked, because he did not understand why it worked. And to a man like Planck, a formula you cannot explain is not really an answer. It is just a lucky guess. So he sat down to figure out what had to be true about the world in order for his formula to come out right. And what he found is the moment everything changed. Here is the move he had to make, and I want to go slow on it, because this single idea is the seed that the entire rest of this video grows out of. Planck imagined the walls of the hot box as being full of tiny little oscillators, little things that wiggle back and forth and give off light as they wiggle. And under the old rules, one of these oscillators could hold any amount of energy at all. It could have a tiny sliver of energy, or a little more, or a little more than that, smoothly, with no gaps, the way a ramp lets you stop at any height you want. But Planck found that the only way to make his formula come out right, the only way to kill the ultraviolet catastrophe, was to say that the oscillators could not hold just any amount of energy. They could only hold energy in specific size chunks, not a ramp, but a staircase. You could be on this step, or the next step up, or the step above that, but you could never, ever stand in between two steps. And the size of those chunks, the height of each step on the staircase, depended on the color of the light. For the high colors, the violet and the ultraviolet, the steps were tall, which meant it cost a huge amount of energy just to take a single step up. And that is the whole trick. That is what saves the world from the death ray. Because the high color oscillators needed such a big chunk of energy to do anything at all, and there simply was not that much energy lying around at normal temperatures. Most of them just could not get going. They were stuck on the ground floor, unable to afford even one step, so they gave off no light. The catastrophe at the violet end vanished, not because the math was patched up by hand, but because nature was charging an entrance fee that the high colors could not pay. Planck called these chunks quanta, which is just the Latin word for amounts or how much, and a single one is a quantum. And he found that the size of each chunk was the color's frequency multiplied by a brand new number, a tiny little constant of nature that nobody had ever needed before, which we now call Planck's constant, and write with a little letter h. This number is staggeringly small. It is a decimal point followed by a long string of zeros before you get to any digits at all, which is exactly why we never notice the staircase in everyday life. The steps are so unbelievably tiny that to us, a ramp and a staircase look identical, the way a movie looks like smooth motion, even though it is really a stack of separate still pictures. The graininess is there. It has always been there. It is just far too fine for human eyes to ever pick out. He announced this on the 14th of December in the year 1900 at a meeting of the German Physical Society in Berlin, and that date is the one physicists usually point to as the birthday of the whole field. But here is the part I love. Planck did not believe his own idea. He thought the chunks were a mathematical trick, a bookkeeping convenience, something he had been forced to do to make the numbers work. And he fully expected that someday someone would come along and explain it in a sensible way that let the energy go back to being smooth. He once described the whole thing, looking back years later, as an act of desperation, and he meant it. He wrote that he had been willing to sacrifice any of his old beliefs about physics just to get an answer at any price. He had cracked open a door he did not want to open, and then he spent a long time trying to push it shut again. But the door was open now, and the next person to walk through it was a 26-year-old patent clerk who had no intention of being polite about it. The patent clerk was Albert Einstein, and in 1905 he was not famous yet. He was just a young man working in a patent office in Switzerland, reviewing other people's inventions during the day and thinking about physics in his spare time. That one year, 1905, is the most ridiculous year any scientist has ever had, because in those 12 months, Einstein published a handful of papers that each on their own would have made a career, including the one that gave us the most famous equation in the world, the one about energy and mass. But the paper that matters for our story, and the one that he himself later called genuinely radical, was not about relativity at all. It was about light, and about the strange little effect that nobody could explain. The effect was this: if you shine light onto a piece of metal, the light can knock electrons right out of the surface, like a hose knocking leaves off a sidewalk. This is called the photoelectric effect, and by itself it was not surprising, because if light is a wave carrying energy, then sure, a wave hitting metal could shake electrons loose. But when people actually measured it carefully, the details made no sense under the wave picture. Under the old wave idea, a brighter light carries more energy, so a brighter light should kick the electrons out harder and faster. That is not what happened. Making the light brighter knocked out more electrons, sure, but it did not make any of them come out with more energy. Instead, the energy each electron came out with depended only on the color of the light, not the brightness at all, and it got stranger. If you used a reddish light, no electrons came out, none, no matter how blindingly bright you made it. You could crank a red lamp up to the power of the sun and still nothing would happen. But the moment you switched to a bluer light, even a dim and feeble one, electrons started popping out immediately, with no delay at all. So somehow the color was the thing that mattered, and there was this sharp cutoff, a line in the colors where below it nothing happened ever, and above it things happened instantly. The wave picture of light had no way to explain that. A wave should be able to slowly build up enough energy to free an electron if you just waited long enough, and a brighter wave should always beat a dimmer one. Nature said no on both counts. Einstein looked at this and made a leap that even Planck was not willing to make. Planck had said the oscillators in the wall gave off energy in chunks, but he still thought of the light itself, once it was traveling, as a smooth wave. Einstein said, no, the light itself is the chunks. Light is not a continuous wave at all when it comes to these interactions. It is a stream of little packets of energy, little bullets, and each packet carries an amount of energy set by its color, exactly the chunk size that Planck had stumbled onto. We now call these packets photons, and once you think of light that way, the whole strange puzzle just dissolves and makes perfect sense. Watch how cleanly it works. One photon hits one electron and hands over all its energy in a single transaction, like one coin going into a slot. A reddish photon is a low-value coin. It simply does not carry enough energy to pay the price of freeing an electron from the metal. So no matter how many of these cheap coins you throw at the surface, which is what making the light brighter means, none of them individually can do the job, and the electron never comes loose. A bluer photon is a high-value coin. It carries more than enough to free an electron in one hit, so even a single one will do it instantly, which is why a dim blue light works and a blazing red one does not. And making any light brighter just means sending more coins per second, which frees more electrons, but never changes how much each individual electron walks away with, because each electron only ever got hit by one coin. Every weird detail of the experiment falls right into place. Now, this should have been celebrated, but instead it made Einstein look a little reckless, because he was saying something that flew in the face of 100 years of solid evidence. Light being a wave was not some shaky guess. It was rock solid, proven over and over. Maxwell's equations said light was a wave. The way light bends and spreads and forms those rainbow interference patterns when it goes through narrow slits, that is wave behavior through and through, and you cannot explain it with bullets. So Einstein was, in effect, claiming that light was a wave when you did one kind of experiment and a stream of particles when you did another kind, and that just sounded like a contradiction, like saying something is both a circle and a square. Most physicists, including some great ones, did not buy it for years. Even when they used Einstein's photon idea to make predictions, they often did it while privately hoping somebody would find a way to make the particles go away. But the photons did not go away because the predictions kept coming true. And here is the lovely twist in the timeline. When Einstein finally won the Nobel Prize, which happened in 1921, though they actually handed it to him in 1922 while he was traveling through Japan. They did not give it to him for relativity, the thing he is most famous for. The relativity work was still thought to be a little too wild and unproven for a prize. They gave him the Nobel specifically for explaining the photoelectric effect for the photons. So the most famous scientist who ever lived got his only Nobel Prize for the one idea he had that he himself called revolutionary, the idea that light comes in chunks. And the contradiction at the heart of it, the business of light being a wave and a particle at the same time, did not get resolved by that prize. It got deeper, because soon someone was going to show that it was not just light that lived this double life, it was everything. While all of this was going on, there was a completely separate mess brewing over in the world of atoms, and it is worth walking through because it is the next big crack in the old picture, and it leads us straight to one of the most important pieces of the whole puzzle. By the early 1900s, people had worked out that atoms were not solid little balls. They had parts inside. A New Zealand-born physicist named Ernest Rutherford had done a famous experiment where he fired tiny particles at a thin sheet of gold foil, expecting them to sail straight through, and most of them did. But every now and then, one would bounce almost straight back, which shocked him. He said it was about as believable as firing a large shell at a sheet of tissue paper and having it come back and hit you. The only way to explain those bounces was that almost all of the atom is empty space, with nearly all its mass crammed into a tiny dense lump right at the center, which we now call the nucleus, with the lightweight electrons somewhere out around it. So the picture people settled on was a little solar system. A heavy positive nucleus sitting in the middle like the sun, and the negative electrons whizzing around it in orbits like planets. It is a tidy image. It is the image you probably still see on signs and logos for anything science related, and it is also completely impossible, which everybody realized almost immediately. Here is the problem. Maxwell's rules, the same beautiful rules about electricity and light, say that whenever you take an electric charge and force it to move in a curve, it has to give off light. And giving off light means losing energy. An electron circling a nucleus is a charge moving in a curve constantly, so it should be constantly bleeding away energy as light, spiraling inward faster and faster, and crashing into the nucleus in a tiny fraction of a second. Every atom in the universe should collapse in far less than the blink of an eye. And yet, here we all are, made of atoms that have been sitting around perfectly stable for billions of years. So the solar system atom was a disaster, under the old physics, just like the hot glowing box had been. And there was a second puzzle stacked right on top of it. When you take a pure gas of one kind of atom, like hydrogen, and you heat it up so it glows, and then you spread that light out into a rainbow, the way a prism does, you do not get a smooth, continuous rainbow. You get a few sharp, bright lines, sitting at very specific colors, with darkness in between. Each kind of atom has its own pattern of lines, like a barcode, completely unique to that element, so reliable that this is literally how we figure out what distant stars are made of. But nobody had any idea why an atom would only give off a few exact colors instead of a smooth spread. Where were those specific colors coming from? Why those and not others? The man who tied these two mysteries together was a young Danish physicist named Niels Bohr, who is going to be one of the central figures for the rest of this whole story. So it is worth meeting him properly here. Bohr was thoughtful, slow-speaking, famously hard to understand even for the people who worked with him, and absolutely fearless about throwing out old rules when the evidence demanded it. In 1913, he took Planck's chunky energy idea and Einstein's photon idea, and he aimed them straight at the atom, and he made a bold guess that turned out to be almost right. Bohr said that the electrons cannot orbit at just any distance from the nucleus. They are only allowed to sit in certain specific orbits, certain specific rungs, and nothing in between. The same staircase idea Planck had been forced into. An electron sitting in one of these allowed orbits, against everything Maxwell said, simply does not give off any light and does not spiral in. It just stays there, stable, as long as nothing disturbs it. That one rule, stated flatly with no deeper justification, saved the atom from collapse, and then Bohr explained the barcode of colors with a second piece. An electron can jump from one allowed orbit to another, but to jump down to a lower rung, it has to get rid of exactly the right amount of energy, and it dumps that energy out as a single photon. Since the rungs are at fixed energies, the gaps between them are fixed too, so the photons that come out can only have certain specific energies, which means only certain specific colors. The barcode was a map of the staircase. Each bright line was an electron falling from one particular rung down to another particular rung, releasing one particular photon every single time. And the amazing thing is that Bohr could do the arithmetic and predict the exact colors in hydrogen's barcode, the precise positions of the lines that experimenters had been measuring for decades with no explanation, and his numbers came out right. That is the moment people really started to take the chunky quantum world seriously, because here it was making a hard prediction about something you could measure in a lab, and it nailed it. But Bohr's model, for all its success, was still a patchwork. It worked beautifully for hydrogen, the simplest atom with a single electron, but it stumbled on anything more complicated. And worse, nobody could say why the orbits were quantized. Bohr had just declared that they were by decree, because it worked. It was a rule with no reason underneath it. The reason was still missing, and finding it would take a strange idea from a French aristocrat who had originally trained to be a historian. The French aristocrat was Louis de Broglie, an actual prince from an old noble family who had started out studying history before the pull of physics got him. And in 1924, in his doctoral thesis of all places, he asked a question so simple and so strange that his examiners did not quite know what to do with it. The question went like this: we have just spent 20 years learning that light, which everybody was certain was a wave, also behaves like a stream of particles. So if a wave can act like a particle, then why not the other way around? Why can a particle not act like a wave? Why should the strangeness only run in one direction? And then he took it all the way and said that every piece of matter, every electron, every atom, every object has a wave that goes along with it, with a wavelength you can calculate from how fast and how heavy the thing is. Now, on the face of it, this sounds like nonsense, because you do not see a baseball ripple and spread out like a wave when you throw it, and you do not see a person diffract when they walk through a doorway. But the Broy's formula explained that too, because the heavier and faster a thing is, the smaller its wavelength gets. And for anything as big as a baseball or a person, the wavelength is so unimaginably tiny that the wave behavior is completely invisible, just like Planck's energy steps were too small to see. The wave is there, the math says. It is just utterly undetectable for big things. But for something as light as an electron, the wavelength is large enough to actually matter, large enough to show up in an experiment. And here is the part that makes de Broy's idea more than just a wild guess, because it did something beautiful. It explained Bohr's mysterious orbits. Here is how that works. If an electron going around the nucleus is really a wave wrapped around in a circle, then for that wave to survive, it has to meet up neatly with its own tail, so that the crests line up with crests and the wave reinforces itself instead of canceling itself out. Only certain sized orbits let the wave fit around the whole number of times without clashing with itself, the way only certain notes ring out cleanly on a guitar string, while everything in between just produces a dead buzz. So the allowed orbits were not arbitrary after all. They were the orbits where the electron's wave fit perfectly, like standing waves on a loop of string. Bohr's mysterious rule, the one he had just declared without explanation, suddenly had a reason underneath it, and the reason was that matter is wavy. When de Broglie's thesis landed on the examiner's desks, they were genuinely unsure whether it was brilliant or ridiculous, so they sent it to Einstein to get his opinion. And Einstein read it and said that de Broglie had lifted a corner of the great veil. With that endorsement, the idea was taken seriously, and within just a few years, experimenters confirmed it directly. They fired beams of electrons at crystals, and the electrons came out the other side, forming exactly the kind of spreading, overlapping pattern that only waves can make. The same kind of pattern light makes. Electrons, these things everybody had pictured as tiny, hard pellets, were diffracting and interfering like ripples on a pond. The wave nature of matter was no longer a guess from a history student. It was sitting right there in the data, and that meant the contradiction at the heart of light, the wave that is also a particle, was not some special weird thing about light. It was the way everything in the universe works, all the way down, which raises a question that is going to drive the rest of this entire story. If a single electron is somehow a wave of what exactly? A wave made of what stuff? Hold on to that question, because the answer is the single strangest thing in all of physics, and we are getting close to it now. There is one experiment that sits right at the center of all of this. One experiment that the great physicist Richard Feynman said holds the only mystery of quantum mechanics, the one thing you can never explain away, the heart of the whole business. He said that once you really understand this one experiment, you understand basically everything strange about the quantum world, because every other weird thing is just a version of this. So, I want to slow all the way down here and walk through it as carefully as I possibly can, because if you only take one thing away from this entire video, this is the thing. It is called the double slit experiment, and it starts off looking almost boringly simple. Way back in 1801, long before any of this quantum business, an English polymath named Thomas Young did this experiment to settle the argument about whether light was a wave or a stream of particles. And at the time, it looked like he had proven once and for all that light is a wave. Here is the setup. You take a source of light and you shine it at a barrier that has two narrow slits cut into it, side by side, close together. On the far side of the barrier, you put a screen to catch whatever comes through. And then you look at the pattern that builds up on that screen. The question is, what do you see? If light were made of little pellets like tiny bullets, the answer would be obvious. The bullets would fly through one slit or the other, and you would get two bright stripes on the screen, one lined up behind each slit, exactly where the bullets that made it through would land. Two slits, two stripes, done. But that is not what you get. What you actually see on the screen is not two stripes. It is a whole series of bright stripes and dark stripes, alternating, many of them, spreading out across the screen, a pattern that physicists call interference fringes. And this pattern is the unmistakable fingerprint of waves, because it is exactly what waves do. Let me make sure the wave part is clear, because everything hangs on it. Picture dropping two stones into a still pond at the same time, a little apart. Each one sends out a circle of ripples, and those two sets of ripples spread out and run into each other. In some places, a crest from one set meets a crest from the other, and they add up into a bigger crest. In other places, a crest from one meets a trough from the other, a high point meeting a low point, and they cancel each other out completely, leaving the water flat and still. So where the two sets of ripples overlap, you get this woven pattern of reinforcement and cancellation. That is exactly what the light does coming through the two slits. The light wave goes through both slits at once. The two waves spread out and overlap on the far side, and where crest meets crest, you get a bright stripe, and where crest meets trough, you get a dark stripe with no light at all, even though light is pouring through both slits. The dark stripes are the places where light plus light somehow equals darkness, because the waves are canceling. That cancellation is the proof. Bullets can never cancel each other out. Only waves can. So, Young's experiment looked like the final word, and for 100 years, light was a wave. Case closed. Now we bring in everything we have learned, and this is where the floor drops out from under you. We know now, from Einstein and the photoelectric effect, that light is also made of particles, of photons. So let us do something Young could never have done. Let us turn the light source down, dimmer and dimmer, until it is so faint that it is only sending out one single photon at a time. One lonely photon leaves the source, travels to the barrier, and either gets through or does not. And then we wait, and then we send the next one, all alone, long after the first one is gone. There is never more than one photon in the whole apparatus at any moment, so there is nothing for it to interfere with. It cannot meet a crest or a trough from another wave, because there is no other wave. There is just it by itself, crossing an otherwise empty machine. Each photon, when it lands, makes a single tiny dot on the screen. One little point, exactly like a particle would. So far, so good. That looks like a bullet. We see one dot, then later another dot, then another, scattered around, one at a time, each one a clean single hit. But then you let it run. You send through one photon after another, thousands of them, then millions, each one completely alone, each one landing as a single innocent dot. And you watch where the dots pile up, and slowly, dot by dot, the pattern that builds up on that screen is the interference pattern, the bright stripes and the dark stripes, the exact woven fringe pattern that only waves can make. The dots avoid the dark stripes and crowd into the bright stripes, building up the wave pattern out of individual particle hits, even though no two photons were ever in the machine at the same time to interfere with each other. Sit with how insane that is, because it is genuinely one of the strangest facts ever discovered. Each photon went through the apparatus completely alone. There was nothing else there, and yet somehow each lonely photon knew to avoid the spots that are dark in the wave pattern and to favor the spots that are bright. A single photon by itself produced interference, but interference is two waves canceling and reinforcing. So what was the single photon interfering with? The only answer that works, the answer the math forces on you, is that the single photon went through both slits at the same time. It did not go through the left slit or the right slit. It went through both as a wave, spread out, overlapping with itself, canceling and reinforcing against itself. And then it landed as a single dot, a particle again, in a spot allowed by its own self-interference. One thing taking every path at once, and then collapsing down to a single point when it arrives. Now, maybe you are thinking, all right, that is weird for light. Light was always a bit slippery, but surely a solid little electron does not pull this kind of trick. And that is the part that should genuinely unsettle you. So I will say it gently. They did the exact same experiment with electrons, firing them one at a time at a barrier with 2 slits, each electron leaving the gun completely alone and landing as a single dot on a detector. And the electrons did the same thing, one at a time, alone, never 2 in the machine together. They built up, dot by dot, the same interference pattern. Each single electron went through both slits at once and interfered with itself. This has been done in the lab many times, and there is footage of it, where you watch the screen start out as a scatter of random looking dots, and then slowly, as the count climbs into the thousands, the stripes emerge out of the noise like a photograph developing. It is one of the most beautiful and disturbing things you will ever see. And it is not light, it is matter, the stuff you are made of, behaving like a wave that goes 2 ways at once. So now we are really stuck with the question from before. The electron is spread out like a wave going through both slits, but when it hits the screen, it is a single dot in a single place. A wave of what, then? A wave made of what? This is the question that an Austrian physicist was about to answer, and his answer is so strange that nearly a century later, people are still arguing about what it actually means. But before we get to his answer, I have to show you the single most upsetting version of this experiment, the one that takes the weirdness and turns it into something that feels almost personal, because it brings in the one ingredient we have been dancing around, which is the act of looking. Here is the version that breaks people's brains. We have got our 2 slits and we are firing electrons through one at a time, and we are getting the interference pattern, which tells us each electron is somehow going through both slits at once. Naturally, a sensible person wants to catch it in the act. So you set up a little detector at the slits, a tiny instrument that watches and tells you which slit each electron actually went through. You are not blocking anything, you are not changing the path. You are just peeking, just gathering the information about which way it went. And you run the experiment again, watching this time, and you check which slit each electron passed through, and the detector dutifully tells you left, right, left, left, right. A clean answer every single time. Each electron went through exactly one slit, like a respectable particle should. Good. Now look at the screen. The interference pattern is gone. The stripes have vanished. Instead, you get 2 simple blobs, one behind each slit, exactly the boring palette pattern you would expect from little bullets. The moment you set up a way to know which slit the electron went through, it stops going through both. It stops being a wave and starts being a particle, and it picks one slit, and the self-interference disappears completely. And then, if you switch the detector off, if you stop gathering the which slit information, the interference pattern comes right back. stripes return. Turn the watcher on, particle, 2 blobs. Turn the watcher off, wave, many stripes. You can flip it back and forth. The behavior of the electron depends on whether or not its path is being recorded. I need to head off the obvious objection here because everybody has it, and it is a good objection. You might think, well, of course, the detector physically bumped the electron, it nudged it, it disturbed it, and that is what wrecked the pattern. And for a long time, that was a reasonable thing to think. And in many real setups, the detector does disturb things. But physicists got cleverer and cleverer about this, designing gentler and gentler ways to get the witch path information, ways that barely touch the electron at all, and even versions where they delay the decision until after the electron has already passed the slits and the result holds up. It is not really about a physical bump. It is about the information. If the universe contains a record of which slit the electron went through, you get particles and 2 blobs. If no such record exists anywhere, you get the wave and the stripes. The deciding factor is whether the which way information exists, not whether anything physically thumped the particle. It is as if the electron will only commit to being in one place once its path becomes part of the world's knowledge, and until then it stays smeared across all its options. That is the whole mystery, right there. That is the thing Feynman said you can never truly explain. A single object goes through 2 openings at once, interferes with itself, behaves like a spread out wave until the moment its path could be known, at which point it snaps down into a single definite particle, taking a single definite route. The world is fuzzy and many-sided when nobody is checking, and sharp and singular when somebody is. Now we can finally ask the Austrian his question. A wave of what? The Austrian was Erwin Schrödinger, and the story goes that he worked out his big idea over a holiday in the mountains in the winter of 1925, going into 1926. And there is a long-running rumor, which I cannot prove, and you should take lightly, that he had a companion with him on that trip who was not his wife, and that whatever the inspiration was, he came back down the mountain with one of the most important equations in the history of science. What Schrödinger did was take de Broglie's idea that matter is wavy and turn it into a precise piece of machinery. He wrote down an equation, now called the Schrödinger equation, that describes how the wave attached to a particle changes and moves and spreads over time. Give it a starting wave, and the equation tells you exactly and smoothly what that wave does next. The way Newton's rules told you what a cannonball does next. The thing the equation describes, the wave itself, is called the wave function, and it is the central object of all of quantum mechanics, so it is worth getting a feel for it. The wave function is a kind of mathematical shape spread out across space that contains everything there is to know about a particle. For an electron in an atom, the wave function is not a little ball on a track. It is a cloud, a smeared out shape filling the space around the nucleus, thicker in some places and thinner in others. And when Schrödinger took his equation and applied it to the hydrogen atom, something wonderful happened. The allowed energy levels, the rungs of Bohr's staircase, the ones Bohr had just declared by decree with no reason, fell right out of the equation naturally, as the only wave shapes that fit and held steady, exactly the way certain notes are the only ones that ring cleanly on a string. Bohr had to assume the staircase. Schrödinger's equation produced it from the wave, with no extra assumptions at all. That is the moment the staircase finally had a real foundation under it. And the equation worked. It worked spectacularly. It reproduced everything Bohr had gotten right about hydrogen, and then it kept going and explained the more complicated atoms that Bohr's patchwork model had choked on. To this day, when you want to predict how atoms and molecules and chemicals behave, the Schrödinger equation is the tool you reach for, and it is the foundation of essentially all of chemistry. You could write down the equation and grind through the math and predict the behavior of matter to staggering precision. So, in terms of getting the right answers, the wave picture was a triumph beyond anyone's hopes. There was just one small problem that nobody could agree on, and it is the same problem we keep circling back to. What is the wave? What is actually waving? Schrödinger himself thought at first that the wave function was the particle, that the electron really was a smeared out cloud of stuff, a little blob of charge spread through space, and that the wave was the physical reality. It is a clean, comforting idea. It is also wrong, and the man who showed it was wrong handed us the most unsettling rule in all of science. That man was Max Born, a German physicist, and in 1926 he proposed an interpretation of the wave function that Schrödinger hated, that Einstein hated, and that turned out to be right. Born said the wave function is not the particle, and it is not a blob of spread out stuff. The wave function is a wave of probability. It does not tell you where the particle is. It tells you the chance of finding the particle in any given spot if you go looking. Where the wave function is large, you are very likely to find the particle. Where it is small, you are unlikely to find it. And where it drops to zero, like in those dark stripes in the double slit pattern, you will never find it at all. The wave is not made of matter. It is made of odds. Now go back to the double slit with this in hand and watch how it clicks together. The single electron's wave function, its cloud of probability, really does pass through both slits, spreads out, and interferes with itself on the far side, building up a pattern of places where the particle is likely to land and places where it cannot land, but the electron itself is not spread out. When it hits the screen, it shows up at one single spot chosen at random, with the odds set by the height of the wave at each point. Fire one electron, you get one dot somewhere the probability wave allowed. Fire a million, and the dots pile up into the shape of the probability wave. The bright stripes where the odds were high, and the dark stripes where the odds were zero. The wave guides the odds. The particle obeys the odds. And which exact spot any single electron picks is, as far as anyone has ever been able to tell, completely and truly random. I really want you to feel the weight of that, because it is easy to nod past it. Under Newton's old clockwork, randomness was never real. It was just a measure of your own ignorance. A coin flip looks random, but if you knew the exact force on the coin and the exact air currents and the exact spin, you could predict heads or tails every time with certainty. The randomness was only in your missing information, not in the coin. The universe itself always knew the answer. What Born was saying, and what every experiment since has backed up, is that quantum randomness is not like that. It is not your ignorance. When an electron lands at one spot rather than another, there is no hidden information anywhere, not even in principle, that determined where it would go. The universe itself did not know in advance. It genuinely rolled the dice the moment you looked. The randomness is baked into the world at the deepest level, not into your knowledge of it. This is the thing that broke Einstein. This was the bridge he would not cross. He had helped build the quantum world. He had been one of its first and bravest champions back when the photon was a heresy. But a universe that runs on genuine chance, where God plays dice, was something he could not accept. And he said exactly that in a letter to Max Born at the end of 1926. He wrote that the theory delivered a lot, but hardly brought us closer to the secret of the old one, and that he, at any rate, was convinced that God does not play dice. He spent the rest of his life looking for the hidden machinery underneath, the secret gears that would make the dice rolling go away and turn the world back into a clock. He never found it. And much later, long after he was gone, experiments would prove, about as firmly as anything in science ever gets proved, that the gears he was looking for are not there. The dice are real. But we are getting ahead of ourselves, because to understand how they proved that, we first have to meet the rule that made the randomness official and the young man who found it. There is a piece of the timeline I have been holding back because it deserves its own moment. About a year before Schrödinger wrote down his wave equation, a young German physicist named Werner Heisenberg, who was only in his early 20s, had already built a complete and working version of quantum mechanics, and he had done it from a totally different direction. Heisenberg, the story goes, was suffering badly from hay fever in the summer of 1925, and went off to a barren little island in the North Sea called Helgoland to get away from the pollen. And while he was there, working alone late at night, he put together a strange, new kind of math that could predict the behavior of atoms. His approach did not use any picture of waves or orbits or clouds at all. In fact, Heisenberg thought it was a mistake to picture the inside of an atom at all, since you cannot see it, and he insisted on building the theory only out of things you could actually measure, like the colors of light an atom gives off. The math he used was unusual and clunky and involved big grids of numbers, and it came to be called matrix mechanics. So, for a brief and confusing stretch, there were two completely different looking quantum theories sitting side by side. Heisenberg's grids of numbers with no pictures, and Schrödinger's smooth, flowing waves. They looked nothing alike, and there was some real rivalry about it, with Schrödinger saying he was repelled by Heisenberg's math, and Heisenberg saying he found Schrödinger's waves disgusting, which is a wonderfully petty thing for two geniuses to say about each other. But then it was shown by Schrödinger and others that the two theories were secretly the exact same theory wearing different clothes. They always gave the same answers because underneath they were the same thing described in two different languages. That is usually a sign in physics that you have stumbled onto something true, when two people coming from opposite directions arrive at the identical place. But Heisenberg's biggest gift to the world came in 1927, and it is probably the one piece of quantum mechanics that has leaked the furthest out into everyday conversation, usually mangled. So let us get it right. It is called the uncertainty principle. Heisenberg found that there are certain pairs of things about a particle that you simply cannot both know precisely at the same time, no matter how good your instruments are, no matter how clever you get. The most famous pair is position and momentum, which is just a particle's location and how it is moving. The principle says that the more precisely you pin down where a particle is, the more fuzzy and uncertain its motion necessarily becomes. And the more precisely you pin down its motion, the more its location smears out and becomes impossible to nail down. You can trade one for the other, but you can never have both sharp at once. There is a hard limit set by Planck's little constant on the total sharpness allowed. And here is the part everybody gets wrong, so I want to be careful. This is not about your measuring tools being clumsy and disturbing the particle, although that is the way it often gets explained, and even the way Heisenberg first described it. It goes deeper than that. The uncertainty is not in your knowledge of the particle. It is in the particle itself. A particle does not secretly have both an exact position and an exact motion that you are just too clumsy to read off. It genuinely does not possess both sharp values at the same time. This falls right out of the wave picture, actually, because a wave that is bunched up tightly into one small spot, so it has a clear location, is necessarily made of a messy jumble of different wavelengths. And wavelength is tied to motion, so its motion is smeared, and a wave with one clean wavelength and therefore one clean motion is, by its nature, spread out across all of space, so it has no single location. You cannot have both, not because you are clumsy, but because that is what it means to be a wave. The fuzziness is a feature of reality, not a flaw in the ruler. This is also, by the way, what really saves the atom from collapse, deeper than Bohr's decree. If an electron tried to spiral all the way down and sit perfectly still right on top of the nucleus, it would have an extremely precise position pinned to a tiny spot, and the uncertainty principle says that would force its motion to become wildly, enormously uncertain, which means huge energies trying to fling it back out. So there is a standoff, a balance between the pull dragging the electron in and the uncertainty fighting to keep it from being pinned down. And that standoff settles at a certain size. And that size is the size of the atom. The reason matter takes up space at all, the reason you do not fall through your chair, the reason atoms are not infinitely tiny is, in large part, this principle that says you cannot squeeze a particle into a perfectly definite spot without it pushing furiously back. The solidity of the everyday world rests on a rule about what cannot be known. So, by around 1927, all the pieces of the machine were on the table. There was Schrödinger's equation telling you how the wave function smoothly evolves. There was Born's rule telling you the wave function gives you probabilities. And there was Heisenberg's principle telling you there are limits on what can be sharp at once. The machine worked, it made predictions, and the predictions came true every single time. But there was a gaping hole in the middle of it. A hole that has never really been filled to this day, and it is called the measurement problem. And it goes like this. The Schrödinger equation describes the wave function spreading out, splitting, going through both slits, being in many places and many states at once. A smooth, gentle, predictable spreading. That is what the equation does, always, as long as nobody is looking. But the instant you actually measure the thing, the instant you check where the electron landed, you never find it spread out. You find it at one spot. The whole spread out wave of possibilities seems to instantly snap down to a single, definite reality, picked at random with Born's odds, and all the other possibilities just vanish. This snapping down has a name. It is called the collapse of the wave function. And here is the uncomfortable part. Nothing in the Schrödinger equation describes it. The equation describes the smooth spreading. It says nothing about any collapse. So you have got two completely different rules running the show. One rule, the smooth equation, for when nobody is looking, and a second rule, the random snap for the moment of measurement. And nobody could say what counts as a measurement, or why looking should trigger a different rule, or what is physically happening when the wave collapses, or even whether it really collapses at all. The answer that became the standard, the one taught in textbooks for generations, came mostly out of Niels Bohr's Institute in the city of Copenhagen, which is why it is called the Copenhagen interpretation, and it is less an explanation than a kind of practical shrug, though a very sophisticated and carefully argued shrug, roughly. It says this: before you measure, it is meaningless to ask where the particle actually is, because it does not have a definite position. It only has the wave function, the spread of possibilities. The act of measurement is what forces nature to commit to one answer. Do not ask what the particle is doing when you are not looking, because that question has no answer you could ever check, and the question you can never check is not really a physics question at all. Bohr was firm about this, to the point of being almost mystical. There is a line attributed to him that there is no deep quantum world. There is only an abstract quantum description, and that it is wrong to think the job of physics is to find out how nature is, because physics only concerns what we can say about nature. Whether that is profound wisdom or a fancy way of refusing to answer the question is something people have been arguing about for nearly 100 years, and you can put me down as genuinely unsure. The state a particle is in before measurement, this business of being in many states at once, has a name too, and it is one you have definitely heard. It is called superposition. A particle in superposition is not in one state or another, with us simply not knowing which. It is, in some hard to swallow sense, in all of them at the same time, the way the electron went through both slits at once. An electron can be spinning in two opposite ways at once. A particle can be in many places at once, and it stays that way, all possibilities layered on top of each other, right up until you measure it, at which point it picks one. Superposition is the wave going through both slits. Collapse is the single dot on the screen. The whole strangeness is the gap between those two, the gap nobody can quite explain. There is one more idea of Bohr's that deserves its own slow moment, because it sits right at the heart of how he made his peace with all of this strangeness, and it is an idea he cared about so deeply that he had it carved onto his family coat of arms near the end of his life. He called it complementarity, and once you see it, a lot of the weirdness we have been circling starts to feel less like a contradiction and more like a feature of how the world is built. The idea is this: a quantum thing has more than one face, more than one way of showing up to us, and some of those faces can never be seen at the same time. Not because our instruments are too clumsy, but because the faces genuinely exclude one another. The way you cannot see both sides of a coin from a single point of view, no matter how good your eyes are. The clearest example is the one we have already met: the way light and matter behave, sometimes like a spread out wave, and sometimes like a hard little particle. Bohr's point was that these two descriptions, wave and particle, are both true and both necessary, and yet you can never catch both in the same experiment. If you set up your apparatus to reveal the wave nature, to show the soft rippling interference, then the particle nature stays hidden. If you set up your apparatus to pin down the particle, to catch it as a single dot going through a single slit, then the wave nature vanishes and the interference disappears. The experiment you choose to do decides which face nature shows you, and you simply cannot build an experiment that shows you both at once. They are complementary, two halves of a whole that can never be laid side by side, each one complete and useful in its own setting, and each one blind to what the other reveals. Bohr thought this was not a flaw in the theory, but a deep truth about reality, maybe even a truth that reached beyond physics. He liked to suggest that the same kind of either-or, this idea of two true descriptions that cannot share a frame, showed up all over the place, in biology, in psychology, even in everyday human life, where the closer you look at one aspect of something, the more another aspect slips out of focus. Whether or not you buy the grand version of the idea, The narrow physics version is solid, and it is one of the genuine lessons of the whole subject. A quantum thing is not secretly a wave that sometimes looks like a particle, and it is not secretly a particle that sometimes looks like a wave. It is something that has no everyday counterpart at all. A thing that answers wave questions with wave answers and particle questions with particle answers, and that refuses, always, to be both things in the same breath. The single word for that refusal, the word Bohr wanted carved in stone, is complementarity, and it is one of the quieter, deeper ideas to come out of all this. This brings us to the most famous animal in the history of physics, and it is worth knowing that the cat was not invented to show how cool quantum mechanics is. It was invented to show how absurd it is. Erwin Schrödinger, the wave equation man, was deeply bothered by the Copenhagen shrug, and in 1935 he came up with a thought experiment to push the weirdness in everybody's face, to take the strangeness that lives down at the level of single particles and blow it up to a size where it becomes obviously ridiculous. He was not saying the world really works this way. He was saying, look at the nonsense your interpretation leads to if you take it seriously. Here is the setup, and remember, it is a thought experiment. No actual cat was ever involved. You put a cat in a sealed box where you cannot see in. Inside the box, you also place a tiny bit of radioactive material, just a small amount, such that over the next hour there is exactly a 50-50 chance that one of its atoms decays. Radioactive decay is a genuinely quantum random event, governed by exactly the probability rules we have been talking about, with no hidden schedule. So, whether or not an atom decays in that hour is a real quantum coin flip. Then you rig up a detector so that if the atom decays, the detector trips a hammer which breaks a flask of poison which kills the cat. If the atom does not decay, nothing happens and the cat is fine. You close the box and you wait 1 hour. Now, according to the quantum rules, that radioactive atom, while nobody is looking, is in a superposition. It is in a blend of both decayed and not decayed at the same time, both possibilities layered together, because that is what unmeasured quantum things do. But the atom is connected to the detector, which is connected to the hammer, which is connected to the poison, which is connected to the cat. So if the atom is in a superposition of decayed and not decayed, then by the same logic, the whole chain is too, and that means the cat sitting in the sealed box would be in a superposition of dead and alive at the same time. Not alive, but we do not know it. Not dead, but we have not checked. Genuinely both, smeared together until the moment you open the box and look, at which point the whole thing collapses and you find one outcome, a living cat or a dead one, picked by the quantum coin flip. That is obviously absurd. And that was the entire point. A cat cannot be both alive and dead. So Schrödinger was asking the hard question that the Copenhagen shrug glosses over. If superposition is real for the atom, where exactly does it stop? Why does the cat get to be definitely one thing, while the atom gets to be both? What is so special about the cat or the detector, or the box, or the person opening it, that it forces a collapse? Where is the line between the fuzzy quantum world of both at once and the sharp everyday world of one thing at a time? Nearly a century later, that line has never been cleanly drawn, and the cat is still sitting in its box, half a punchline and half the deepest unsolved problem in the whole subject. Different interpretations of quantum mechanics are, in a real sense, just different answers to the question of what happens to that cat. And we will get to some of those answers later, because a few of them are even stranger than the cat itself. Now, I want to back up and add in a piece of the puzzle that we have skipped over, because it turns out to be one of the most important properties a particle has, and it is genuinely impossible to picture, which is sort of the point. The property is called spin. The name is a historical accident, and it is honestly a little misleading, because when physicists first ran into this property, they imagined the particle was literally spinning around like a tiny top, and that picture is wrong, but the name stuck, so we are stuck with it. Spin is a kind of built-in magnetism that particles carry, a tiny magnetic character that comes in fixed amounts and points in a direction, and it behaves like nothing in the everyday world. The experiment that revealed it is one of the great ones done by two Germans, Otto Stern and Walter Gerlach, back in 1922. They sent a beam of silver atoms through a specially shaped magnetic field and onto a screen, and the magnetism of each atom should have bent its path. Now, if spin were like a normal spinning top, pointing in random directions, you would expect the atoms to get bent by all different amounts, smeared into a single continuous smudge on the screen, because the tops would be tilted every which way. That is not what happened. The beam split cleanly into exactly two spots, one up, one down, with nothing in between. Every single silver atom was forced to be either fully up or fully down, never sideways, never part way, just the two choices. The magnetism could only point one of two ways. That is the staircase again, the chunkiness, showing up in a brand new place. Spin is quantized. It does not come in a smooth range. It clicks into discrete settings. And spin shows the superposition weirdness as cleanly as anything. If you measure an electron's spin along the up and down direction, you always get either up or down, 50-50 fine. But now take an electron you have measured as up and measure its spin along a sideways direction, instead left and right. You get left or right, 50-50, totally random again. And now comes the strange part, because if you then go back and measure the original up and down direction one more time, the electron has forgotten its earlier answer, and it is back to 50-50, up or down. Income, even though you measured it as definitely up just moments ago. Measuring the sideways spin scrambled the up and down spin completely. The two measurements interfere with each other, because a particle cannot have a definite spin in two different directions at the same time, just like it cannot have a definite position and motion at once. Spin is where a lot of the cleanest modern quantum experiments are done because it is so simple. Just two outcomes, up or down, the most basic quantum coin you can build. Spin leads directly into one of the most consequential rules in all of physics, and it explains something you probably never thought needed explaining, which is why matter is solid and why there is any chemistry or any chemistry-based life at all. The rule was worked out by an Austrian physicist named Wolfgang Pauli, who was famously sharp-tongued and so feared for his criticism that there was a running joke among physicists about the Pauli effect, the idea that equipment would mysteriously break just because he walked into the room. In 1925, Pauli figured out a rule now called the exclusion principle, and it says that no two electrons in an atom can be in the exact same quantum state at the same time. They are not allowed to pile up together. Each one has to occupy its own distinct rung, its own distinct configuration, and once a spot is taken, no other electron can have it. This sounds like a dry piece of accounting, but it is the reason the entire periodic table exists, which is to say, it is the reason there are different chemical elements with different personalities at all. As you build up bigger atoms with more and more electrons, the electrons cannot all just crowd down into the lowest, coziest energy level, because the exclusion principle forbids it. So they are forced to stack up into higher and higher levels, filling the rungs one pair at a time. And the way the outermost electrons are arranged is what gives each element its chemical character. What makes oxygen behave like oxygen, and gold behave like gold, and carbon able to build the molecules of life. Every difference between every element traces back to electrons being forbidden from sharing a state. And on top of that, this same principle is a big part of why solid matter resists being squished. When you push your hand against a table, the electrons in your hand and the electrons in the table cannot merge into the same states, so they push back hard. And that resistance is a real part of what you feel as solidness. You do not fall through your chair in large part because of a quantum rule from 1925 about electrons refusing to share. Whole dead stars, the ones called white dwarfs, are held up against the crushing pull of their own gravity by nothing but this stubborn refusal of electrons to be squeezed into the same state. A rule about quantum bookkeeping is holding up the corpses of stars. That stubborn refusal of electrons to share a state turns out to point at one of the great dividing lines in all of nature, a split that sorts every particle in existence into one of two camps, two tribes with two completely opposite personalities, and the thing that decides which tribe a particle belongs to is that strange property we just met, the spin. So it is worth pausing on, because it ties together a surprising number of the threads we have been following. On one side, you have the antisocial particles, the loners, the ones that obey Pauli's rule and absolutely refuse to pile into the same state. Electrons are in this camp, And so are protons and neutrons, and so are the even smaller things called quarks that protons and neutrons are built from, and so are the ghostly little neutrinos. These particles are called fermions, named after the Italian physicist Enrico Fermi, and they are the standoffish ones, the ones that insist on their own space. And because they insist on their own space, they are the particles that build up structure. They are the particles that matter is made of. Every solid thing, every atom in your body is a great stack of fermions, all keeping their distance from one another. And that keeping of distance is exactly why matter takes up room and has shape and does not collapse into a point. On the other side, you have the sociable particles, the gregarious ones, the ones that feel no such rule and are perfectly happy to pile up by the millions into the exact same state, all doing the identical thing in the identical place. Particles of light, the photons, are the great example of this camp. So are the particles that carry the other forces of nature, and so is the famous Higgs. These crowd-loving particles are called bosons, named after the Indian physicist Satyendra Nath Bose. And rather than building up matter the way the loners do, they tend to be the particles that carry forces and carry energy, the messengers, rather than the bricks. And whether a particle is a loner or a joiner, a fermion or a boson, comes down entirely to its spin. Particles whose spin comes in the awkward half-sized amounts are always fermions, always antisocial. Particles whose spin comes in whole number amounts are always bosons, always happy to crowd together. There is no in between, and there are no exceptions. And the deep reason why was worked out by Pauli himself years later in a result so important it has its own name, the spin statistics connection. Though the why of it reaches down into mathematics, we will leave gently alone. Once you have this split in your head, a couple of things we have already talked about and a couple we are coming to suddenly make a lot more sense. A laser, for instance, is nothing more than a vast crowd of photons all bullied into the exact same state, marching in perfect lockstep. And a laser can do that precisely because photons are bosons, and bosons love to share a state. You could never make a laser out of electrons because electrons are fermions and would refuse. And later on, we will meet a bizarre form of matter where atoms themselves are chilled down until they all collapse into one shared state and start behaving like a single thing. And that trick only works for atoms that happen when you add up all their pieces to come out as bosons. There is even a lovely case where two different versions of the same element, two kinds of helium, end up in different tribes, one a loner and one a joiner, just because of how their inner pieces add up, and the two of them behave so differently at very cold temperatures that you would hardly know they were the same stuff. The whole universe, in a sense, is built out of these two temperaments, the bricks that keep apart and the messengers that pile together, and the line between them is drawn by spin. Now that we are talking about electrons stacking up into their separate states inside an atom, it is worth slowing right down and looking at what those states actually are. Because the picture most of us got taught as children, the one with little electrons whizzing around the nucleus in neat circles like planets going around the sun, is wrong, and the real picture is so much stranger, and honestly so much calmer once you sit with it. Remember that an electron in an atom is not a tiny ball on a track. It is a wave, a standing wave, wrapped around the nucleus, a three-dimensional cloud of probability that tells you where the electron is likely to be found if you go looking for it. And it turns out that only certain shapes of cloud are allowed. Only certain standing wave patterns fit neatly around the nucleus without canceling themselves out. And each allowed shape is one of these states. The electrons fill up one by one. These shapes are what chemists call orbitals, and the word orbital is a kind of soft echo of the old word orbit, kept around even though the electron is not really orbiting anything. The simplest shape is just a sphere, a fuzzy round ball of probability centered on the nucleus, with the electron most likely to be found somewhere in that round haze. The next kind of shape is stranger. It looks a bit like a dumbbell or like two teardrops meeting tip to tip, with the nucleus sitting right at the pinch in the middle, and there are 3 of these dumbbell clouds in any given shell, one pointing up and down, one pointing left and right, one pointing front and back, all at right angles to each other, like the 3 edges of a room meeting in a corner. After those come even more elaborate shapes, ones that look like clover leaves and rings, 5 of them in their group. And then the shapes get more baroque still as you go further out. The electrons fill these clouds from the simplest and lowest up through the more elaborate and higher, 2 electrons to a cloud, just as the exclusion principle demands. And the whole structure of every atom in your body is really just this nested set of probability shapes, these fuzzy standing waves humming around their nuclei. Here is a small piece of history that I find oddly charming, which is where the names for these shapes came from, because they sound like they ought to mean something deep, and they really do not. Long before anybody understood that electrons were waves, before anybody had any idea what an orbital was, the people studying the light coming off of glowing elements noticed that the bright lines in that light came in families, and they described those families with plain, everyday words based on how the lines looked to them through their instruments. Some lines looked sharp and crisp. Some were the strong principal lines. Some looked diffuse and smeared out, and so on down a list. When physicists much later worked out that these families of light came from electrons living in these different shaped clouds, they just kept the old descriptive letters, the S and the P and the D and the rest, so that to this day the spherical cloud is called an S orbital, and the dumbbell is called a P orbital, not because those letters describe the shapes at all, but because of how some spectral lines happened to look to a few careful observers more than 100 years ago. The names are a little fossil of an older way of seeing carried forward into the modern picture. And the reason any of this matters, the reason it is not just bookkeeping, is that the shape of the outermost clouds, the ones with electrons in them that are furthest from the nucleus and most able to reach out toward other atoms, is what decides how an atom will join up with its neighbors. Chemistry, the whole business of atoms bonding into molecules, of water being water and proteins folding into the machinery of life, is really just the story of these outer probability clouds overlapping, sharing electrons, lining up and locking together. When two atoms form a bond, what is really happening is that their outer orbitals merge into a new shared shape that wraps around both nuclei at once, and the electrons settle into that joint cloud. So every substance you have ever touched, every reaction that has ever happened in your body or in a star or in a test tube comes down to the shapes of these standing waves and the rules about which ones can overlap. The solid, sloshing, colorful chemical world is built entirely out of the geometry of probability. Here is another consequence of all this wave business that sounds like pure fantasy and is responsible for keeping you alive. So it deserves its slow moment too. It is called quantum tunneling. Remember that the particle is described by a wave function, a spread out cloud of probability. And remember that this cloud does not have hard edges. It tapers off gradually. Now, imagine a particle bumping up against a barrier, a wall it does not have enough energy to get over, like a ball rolling toward a hill it cannot quite climb. In the everyday world, the ball rolls partway up, runs out of oomph, and rolls back down. It never gets to the other side. That is just common sense. But the particle's probability cloud does not stop dead at the wall. It pokes into the wall and pokes out a little on the far side, smaller but not zero. And since the wave function is about probabilities, a small but real amount of cloud on the far side means a small but real chance that the particle will simply turn up over there. On the other side of a barrier, it never had the energy to cross. It does not climb over the wall. It does not smash through it. It just, with some probability, appears on the far side, as if it had teleported through. The thinner the wall and the lighter the particle, the better the odds. This is not a theory waiting for proof. It happens constantly, and we have built whole technologies on top of it. And here is the part that should make you look at the sky a little differently, because tunneling is the reason the sun shines. The sun makes its energy by smashing hydrogen nuclei together to build helium, but those nuclei are all positively charged, and like charges, shove each other away hard. The temperature in the core of the sun, as blisteringly hot as it is actually not nearly hot enough to fling those nuclei together with enough force to overcome that shove. By the strict old rules, the sun should not be able to fuse hydrogen at all. It only works because the nuclei tunnel through the barrier between them, appearing on the far side of a wall they could never have climbed, fusing when they had no business fusing. So, every ounce of sunlight that has ever warmed your face, every plant that has ever grown, the entire chain of life on this planet, All of it runs on particles cheating their way through walls. A bit of quantum strangeness that sounds like a magic trick is the reason there is a sky to look up at. Now we come to the strangest thing of all, the piece that Einstein spent his final decades fighting, the piece that took half a century to test, and that finally, in our own time, settled the argument he had with Bohr in a way Einstein would have hated. It is called entanglement, and it is the deepest, weirdest, most genuinely shocking thing in this entire video. So I am going to take it as slowly as I have taken anything. Here is the basic idea. You can create two particles together in such a way that their properties are linked, joined into a single shared quantum state, even after you carry them far apart. The classic example uses spin. You arrange things so that two particles are born together with opposite spins, but, and this is everything, neither one has decided which way it is spinning yet. They are both in superposition, both undecided, both a blend of up and down, with only one firm fact written into the universe, which is that whenever they are measured, they will turn out opposite. If one is up, the other will be down. If one is down, the other will be up. But which is which has not been settled. It is not that one is secretly up and the other secretly down, and we just do not know yet. Neither one is anything yet. Only the relationship between them is fixed. So you take these two entangled particles and you separate them. You send one across the room or across the country, or, in principle, across the galaxy, while the other stays with you. They are still undecided, still linked, still a single shared state stretched across all that distance, and now you measure yours. The instant you do, yours snaps to a definite answer, say up, chosen at random, and at that very same instant, no matter how far away the other one is, it snaps to the opposite answer, down, not after a delay for some signal to travel between them instantly. The moment your particle commits, the distant one commits to the opposite, as if the two of them are still one object, no matter how much space you put between them. Einstein hated this with his whole heart, and in 1935 he teamed up with two younger colleagues, Boris Podolsky and Nathan Rosen, to write a famous paper attacking it. A paper now known by their three initials as the EBR paper. Their argument was sharp. Look, they said, nothing can travel faster than light. That is the bedrock of relativity, my own theory. So when you measure one particle and the other instantly responds from far away, there is no way a signal got there in time to tell it what to do. Therefore, EPR argued the answer must have been there all along. The particles must have left the factory, each carrying a secret hidden instruction, one secretly up and one secretly down from the very beginning. And the quantum theory just does not include those secret instructions, which means quantum theory is incomplete. There is a deeper layer of hidden information underneath it, the secret gears Einstein had been hunting for all along. The gears that would make the spooky instant connection just an illusion and put the dice rolling to rest. Einstein called the alternative spooky action at a distance, and he meant the word spooky as an insult. He was sure the universe could not really work that way. And here is where the story sat, stuck for almost 30 years because the argument between Einstein and Bohr looked like a philosophical standoff with no way to settle it. Either the particles carried secret, hidden instructions, the way Einstein wanted, or the connection was genuinely instant, and the particles genuinely had no answer until measured, the way Bohr and the standard theory said. Both pictures predicted the exact same thing in the experiments anyone could imagine doing, which is opposite results when you measure both particles. There seemed to be no possible test that could tell the two views apart. It was a matter of taste, of philosophy, of which story you preferred. Most physicists just used the equations, got the right answers, and did not lose sleep over which deeper picture was true. And it might have stayed a question of taste forever, except that in 1964, a quiet Irish physicist found a way to turn the philosophy into an experiment. And that is when this whole story turns from arguing into proving. The Irish physicist was John Stuart Bell, who grew up in Belfast in a family that did not have much money, and who worked for most of his career on the practical physics of particle accelerators, doing the quantum foundation stuff almost as a hobby on the side, because the deep questions would not leave him alone. Bell took Einstein's side emotionally. He found the spooky action genuinely distasteful, and he sympathized with the idea that there ought to be hidden instructions underneath, making the world sensible again. But he was a careful thinker, and instead of just arguing about it, he asked whether the two pictures, the hidden instructions picture and the spooky quantum picture, might actually disagree about something measurable after all, if you set the experiment up cleverly enough. And in 1964, he proved that they do. This result is called Bell's theorem, and it is, in my opinion, one of the most profound things any human being has ever figured out. So let me try to give you the flavor of it without any of the math. The trick is to stop measuring the two entangled particles along the same direction every time, and instead to measure them along different angles, and to mix up those angles randomly. Remember, you can measure spin along up and down, or along a sideways direction, or along any angle in between. So imagine both you and a distant partner each have one particle of an entangled pair, and each of you independently randomly picks one of a few different angles to measure your particle along, and you each write down your result, up or down, for each particle. You do this thousands of times with thousands of pairs, randomly choosing angles each time, and then you get together afterward and compare your lists, and you look at how often your answers match and how often they disagree, and crucially, how that pattern of matching changes depending on the combination of angles the two of you happened to pick. Here is Bell's insight, and it is breathtakingly clean. Suppose Einstein was right, and each particle really did leave the factory carrying a complete set of secret hidden instructions. A little hidden answer sheet that says what result it will give for every possible angle you might choose to measure. If that is true, if the answers are all predetermined and written down in advance, and if, on top of that, what you choose to measure on your side cannot instantly affect the particle on the other side, then Bell showed there is a hard mathematical limit on how strongly your results and your partner's results can possibly be correlated across all those different angle combinations. The matching can only be so coordinated and no more. He boiled it down into a precise statement, an inequality, a ceiling, a number that the correlations in any hidden instruction universe can never go above. That ceiling is now called Bell's inequality. And then he calculated what the standard quantum theory predicts for the very same experiment. And quantum theory blows right through the ceiling. It predicts correlations stronger than any hidden instruction universe could ever produce. Correlations that are simply impossible if the answers were written down in advance and the two sides cannot talk faster than light. So the two pictures, which everyone had thought always agreed, actually make different predictions about this one specific kind of experiment. They give different numbers, and that means it is no longer philosophy. It is a measurement. You can go into a lab, do the experiment, count up the matches and the mismatches, and nature itself will tell you which picture is true. Either the correlations stay under Bell's ceiling, and Einstein was right. There are hidden instructions and the world is sensible. Or the correlations break through the ceiling and Einstein was wrong, and the spooky connection is real, and the particles genuinely had no answers until they were measured. There is no longer any room to split the difference. The universe gets to vote. For a few years after Bell published this, almost nobody did anything with it, partly because the experiment was fiendishly hard to actually pull off, and partly because a lot of physicists still thought of this as not quite respectable, as philosophy dressed up. But a small number of people understood that Bell had handed them the chance to answer the deepest question in the subject. The question Einstein and Bohr had argued over for decades with an actual experiment, and they set out to do it. The first person to really go after it was an American physicist named John Clauser, who was something of an outsider and a bit of a rebel, and who, by his own account, actually expected and even hoped that the experiment would prove Einstein right and show the standard quantum theory was missing something. In 1972, working with a colleague, Clauser built a setup using pairs of photons given off by calcium atoms, with the two photons of each pair entangled, and he sent them off in opposite directions to detectors with polarizing filters set at different angles, which for photons plays the same role as measuring spin at different angles. He counted the matches and the mismatches over many thousands of pairs, and he checked where the correlations landed relative to Bell's ceiling. They broke through it. The correlations were stronger than any hidden instruction universe could allow. Quantum mechanics was right and Einstein was wrong, and Clauser, who had been rooting for the other answer, had to report that his own experiment had gone against his hopes. But his result was not airtight, because the early experiments had what physicists call loopholes, little gaps a stubborn skeptic could still wriggle through. Maybe the detectors only caught a biased sample of the photons. Or, more worryingly, maybe the filter angles were set far enough in advance that some slow hidden signal could in principle have traveled from one side to the other and coordinated the results, which would let a sneaky hidden instruction theory still squeak by. To really nail it, you had to close those gaps. That is where the French physicist Alain Aspect came in. Around 1982, working near Paris, Aspect improved the experiment in a way that tackled the most worrying loophole head-on. The clever bit was that he changed the angle of the measurement extremely fast, while the photons were already in flight, switching the settings so quickly and so late that there was no time for any signal traveling at the speed of light to get from one detector to the other and coordinate things. He pulled the rug out from under the idea that the two sides could be secretly communicating, and the correlations still broke Bell's ceiling. Still stronger than any local hidden instruction picture could produce, Einstein's loophole was closing, and the spooky answer kept winning. And then, over the following decades, the experiments got better and better, run by a number of groups, including the Austrian physicist Anton Zeilinger, who pushed entanglement to new extremes, sending entangled photons over great distances between mountaintops and even up to satellites and back, and who pioneered turning these spooky correlations into actual working tools. By around 2015, several teams managed to run versions of the experiment that closed all the major loopholes at the same time in a single setup, leaving the stubborn skeptic with nowhere left to hide. The verdict was in, and it was overwhelming. Bell's ceiling is broken by nature every time, exactly as quantum mechanics predicts. The universe does not run on hidden instructions written in advance. The particles really do not have answers until they are measured. And the connection between entangled particles really is, in some deep sense, instant and beyond the reach of ordinary distance. In 2022, the Nobel Prize in Physics was given to exactly these three people: John Clauser, Alain Aspect, and Anton Zeilinger, for these experiments with entangled photons, for establishing the violation of Bell's inequalities, and for pioneering the science that grew out of it. A prize for settling in the lab with hard numbers, the argument that Einstein and Bohr had carried on for 30 years. Einstein lost. The spooky action he refused to believe in is woven right into the fabric of the world. Now, I have to add one careful note here, because this is the spot where people get overexcited and start saying wild things. This instant connection cannot be used to send a message faster than light. It sounds like it should let you, but it does not, and the reason is subtle but solid. When you measure your particle, you get a random result, up or down, that you cannot control, and your distant partner also just sees random results on their end. Neither of you can tell, just by looking at your own particle, whether the other one has been measured yet. The spooky coordination only shows up later, after you bring the two lists of results together and compare them. And bringing the lists together takes an ordinary message at ordinary speed, so relativity survives. Nothing useful travels faster than light, but the deep connection is real, and the picture of the world where everything has definite properties sitting in definite places, minding its own business, is simply false. That picture died in those experiments, and it is not coming back. All right, so here is the situation we are now in, and it is a genuinely strange place for science to have ended up. We have a theory, quantum mechanics, that is the most successful theory in the entire history of physics. It has been tested more times, in more ways, to more decimal places than anything else humans have ever come up with, and it has never once been caught getting an answer wrong. We trust it so completely that we build the entire modern world on it. And yet, after 100 years, the people who use it every day still do not agree on what it is actually telling us about reality. The equations are crystal clear and everybody agrees on them. The story about what the equations mean, what is really happening underneath, is wide open, and physicists fall into different camps that genuinely disagree. These camps are called interpretations of quantum mechanics, and I want to walk you through the main ones, because they are each, in their own way, completely bonkers, and you get to pick which kind of bonkers you can live with. The first one we have already met, the Copenhagen interpretation, the old standard. It says, roughly, do not ask what is happening when nobody looks, because the question is meaningless, and the wave function collapses to a definite answer when a measurement happens. And that is just a basic feature of the world that you should accept and not poke at too hard. For a long time, this was the default, the thing taught in textbooks, sometimes summed up with the slightly dismissive phrase, shut up and calculate, meaning, stop worrying about what it means and just use the equations to get your answers. It is practical, it works, but it leaves that gaping hole, the measurement problem, the question of what counts as a measurement and why looking should change the rules, sitting right there unanswered. And a lot of people find that deeply unsatisfying because it feels less like an explanation and more like a refusal to give one. Then there's the interpretation that takes the cake for sheer audacity, and it is one a lot of physicists today actually take seriously, which is the part that should worry you. It is called the many worlds interpretation, first put forward by a young American named Hugh Everett in the late 1950s, when he was still a graduate student. Everett looked at the measurement problem and made a radical move. He said, what if the wave function never collapses at all? What if there is no special measurement rule, no snapping down to one answer, and the smooth Schrödinger equation is the whole story, always, with no exceptions? But then, how do we only ever see one result? Because, Everett said, you do not only see one result. All the results happen, every single one. When you measure a particle that was in a superposition of up and down, the universe does not pick one. It splits. In one branch of reality you see up, and in another, equally real branch, a copy of you sees down, and both branches carry right on, fully real, no longer able to talk to each other. So, under many worlds, the universe is constantly splitting, endlessly, every time any quantum choice gets made anywhere, which is constantly everywhere, branching into an unimaginable, ever-growing number of parallel realities, each one containing its own version of everything, including its own version of you. The cat in the box is not both alive and dead in one world. There is a world where the cat lived and a world where the cat died, both equally real, and a copy of you in each one. And when you open the box, you simply find out which branch you are in. There is no randomness in this picture at all, which is the thing that appealed to people, because the equation just rolls along smoothly forever. The price you pay for getting rid of the randomness and the collapse is that you have to accept a near infinite number of parallel universes, constantly spawning off of this one. Some of the smartest people alive think this is the most honest reading of the math. I genuinely do not know what to do with it, and I do not think anyone really does, but I cannot tell you it is wrong, and neither can anyone else, because every branch makes the same predictions for the branch you happen to be in. There is a third major camp, and it is the one that would have made Einstein happiest, called the pilot wave theory, or sometimes the de Broglie-Bohm theory. After Louis de Broglie, who first sketched it, and the American physicist David Bohm, who fully built it out in the 1950s. This one says, the particle is always a genuine particle, a real little thing with a definite position at all times. No fuzziness about where it is. But the particle is guided along by a real wave, the pilot wave, that pushes it around and tells it where to go. And that wave does pass through both slits and does the interfering, steering the definite particle into the bright stripes and away from the dark ones. So in this picture, there is no superposition of the particle itself, no being in two places at once, just a solid particle riding on a guiding wave. And the apparent randomness comes only from our not knowing the particle's exact starting position. It sounds lovely. It restores a sensible world of things with definite locations, and it makes all the same predictions. The catch, the steep price, is that the guiding wave has to be able to respond instantly to things happening far away. So this picture is openly, unapologetically spooky over distance, even more so than the others. It buys you definite particles at the cost of an explicit, built-in, faster-than-light influence steering them. You do not get something for nothing in this subject, ever. Every interpretation makes you swallow something monstrous. You just get to choose your monster. There are still other interpretations beyond these three, with names like the consistent histories approach and the relational view that says a particle's properties only exist relative to other things rather than absolutely, and a family of ideas called objective collapse theories, which propose that the wave function really does collapse on its own, physically at random, more and more likely the bigger the system gets, which would neatly explain why tiny things stay fuzzy and big things like cats are always definite. Some of these objective collapse ideas are interesting because they actually predict slightly different results from standard quantum mechanics in extreme cases, which means, unlike the others, they could, in principle, be tested and ruled out, and people are slowly building experiments to try. But for the most part, choosing between Copenhagen and many worlds and Pilot Wave is, at least for now, a matter of philosophy and taste, because they all make the same predictions for anything we currently know how to measure. The math is settled, the meaning is anybody's guess. 100 years in, the most successful theory ever built is still, at its heart, a mystery to the very people who wield it best. Now, I have been telling you this story mostly the way it was discovered in the 1920s and 30s, but I would be doing you a disservice if I stopped there, because the theory did not stop there. Over the following decades, it grew into something even deeper and even stranger. And this next layer is where our best current understanding of reality actually lives. So let us push on into it slowly. The early quantum mechanics we have been talking about had a problem. It treated particles in a quantum way, all fuzzy and wavy and probabilistic, but it still treated them as a fixed number of little objects moving around, and it did not play nicely with Einstein's relativity. The rules about space and time and the speed of light. Stitching quantum mechanics and relativity together turned out to require a whole new framework, and that framework is called quantum field theory, and it changes the picture in a way that is honestly beautiful. In quantum field theory, the most basic things in the universe are not particles at all. They are fields. A field is something that exists at every point in space, everywhere, all at once, like an invisible fluid filling all of reality. There is a field for each kind of particle. There is an electron field spread through all of space, and a field for the photon, which is just the electromagnetic field you already know, and fields for all the other particles. And a particle in this picture is not a little ball. A particle is a ripple, a little packet of vibration in its field. An electron is a ripple in the electron field. A photon is a ripple in the electromagnetic field. When two particles bump into each other and bounce away, what is really happening is one ripple in one field, stirring up ripples in others. Everything that exists is just patterns of trembling in these fields that soak through all of space. And this is where one of the most stunning predictions in the history of physics came from. In the late 1920s, a brilliant and famously quiet English physicist named Paul Dirac was trying to write down an equation for the electron that obeyed both quantum mechanics and relativity at once. And he succeeded, but his equation had an extra solution he did not ask for, a sort of mirror image electron, a particle exactly like the electron, but with the opposite electric charge. At first, this was embarrassing, an apparent flaw, but Dirac took it seriously and predicted that this mirror particle should actually exist out there in the world. And a few years later, in 1932, an experimenter found it, a particle with the mass of an electron, but a positive charge, now called the positron. Dirac had predicted a whole new form of matter, antimatter, from nothing but the demand that his equation be consistent, and the universe turned out to contain it. Every kind of particle, it turns out, has an antimatter partner, and when a particle meets its antiparticle, they destroy each other in a flash of pure energy. This is not science fiction. We make antimatter in laboratories, in tiny amounts, and it behaves exactly as predicted. Quantum field theory also tells you something unsettling about empty space, about a perfect vacuum with everything removed. It is not empty. Because of the uncertainty principle, those fields filling all of space can never sit perfectly still and quiet. They are always faintly trembling, even with nothing in them, and that trembling means that in truly empty space, pairs of particles and antiparticles are constantly flickering into existence and vanishing again, borrowing a tiny bit of energy for the briefest instant and then paying it back far too fast to ever catch directly. These are called virtual particles, and the seething, restless, never quite still vacuum they create is not just a fantasy because its effects are real and measurable. The frothing of empty space nudges the energy levels in atoms by a tiny amount that we can detect, and it creates a faint attraction between two metal plates held very close together in a vacuum, a pull called the Casimir effect that has been measured in the lab. So even nothing, even perfect emptiness, is alive with quantum activity. There is no such thing as truly empty space. The void itself hums. This whole framework, quantum field theory, became the foundation of what is now called the Standard Model of particle physics, which is the most precisely tested theory we have ever built, and it describes all the known particles and 3 of the 4 forces of nature as the play of these quantum fields. The last great piece of it to be confirmed was a field called the Higgs field, predicted back in the 1960s to explain why some particles have mass at all, and its ripple, the Higgs particle, was finally found in 2012 at the enormous machine in Europe called the Large Hadron Collider, after a search that took decades and cost billions. So, the strange ideas that started with a man reluctantly chopping energy into chunks to explain a glowing box have grown, step by careful step, into a description of reality where everything is ripples in invisible fields, where empty space is never empty, where antimatter is routine, and where the predictions match the measurements to more decimal places than almost anything else in human knowledge. The weirdness did not go away as we learned more. It got deeper and richer, and somehow even more precise at the same time. Before we get to the useful stuff, there is a question that has probably been nagging at you this whole time, and it is a good one, so let us deal with it. If the world is really this fuzzy and wavy and full of things being in many states at once, then why does nothing around you ever act that way? Why is your coffee cup always in one definite spot? Why have you never seen a person go through two doors at once, or a cat be both alive and dead? Where does all the weirdness go when things get big? For a long time, this was lumped in with the measurement mystery and left as a shrug. But over the last few decades, physicists have worked out a big part of the answer, and it has a name: decoherence. And it is worth understanding because it is probably the most important idea in modern quantum thinking that the public has never heard of. Here is the gist. A particle can stay in a clean superposition, going through both slits, being in two states at once, only as long as it stays perfectly isolated, untouched, with its delicate wave kept private and undisturbed. The moment that particle starts bumping into other things, air molecules, stray photons, the warm jostling environment all around it, its private little wave gets tangled up with all of those things, spreading out and leaking into the environment, getting mixed into a vast mess of surroundings that you could never hope to track. And once that happens, the delicate interference, the thing that makes superposition observable, the thing that makes the stripes appear in the double slit, gets scrambled into the noise and effectively washes out. The superposition is not exactly destroyed, but it gets so hopelessly spread into the environment that for all practical purposes, the object behaves like a plain old definite thing in one definite state. And here is why that explains your coffee cup. A single electron kept in a vacuum, isolated, can hold a superposition long enough to show its wave nature. But anything as big as a cup or a cat or a person is made of unthinkable numbers of particles, all constantly bumping into countless air molecules and bathed in light and radiating heat every fraction of every second. So a big warm object gets tangled up with its surroundings almost instantly, in a tiny sliver of a fraction of a second, so fast that it never has a chance to display any quantum fuzziness you could ever catch. The weirdness does not stop being true for big things. It just gets buried so fast and so thoroughly by the constant touch of the environment that it becomes completely invisible. The line between the quantum world and the everyday world is not a sharp wall. It is the speed at which a thing gets tangled up with everything around it. And big warm things get tangled so fast that they look classical to us in every way that matters. This is also exactly why building quantum machines is so brutally hard, because to keep something in a useful superposition, you have to fight off decoherence. You have to keep your delicate quantum thing almost perfectly isolated from a universe that is constantly trying to bump into it and ruin everything. Now I want to bring this all the way back down to the ground, to the world you can touch, because it would be easy to come away thinking quantum mechanics is just a beautiful brain teaser for physicists, abstract and useless. And that could not be more backward. By one common estimate, something close to a third of the entire modern economy rests on technology that only works because of quantum mechanics. This is not a curiosity. It is the foundation under the device you are listening to me on right now. Start with the single most important invention of the last century, the transistor. A transistor is a tiny switch that controls the flow of electricity, and a modern computer chip has billions of them packed onto a sliver of silicon smaller than your fingernail, switching on and off billions of times a second. Every computer, every phone, every piece of digital anything is built out of transistors. And transistors work because of the quantum behavior of electrons in materials called semiconductors, materials that are neither good conductors nor good insulators, but something controllable in between. The whole reason a semiconductor behaves the way it does, the reason you can nudge it to allow or block electricity on command, comes straight out of the quantum staircase of allowed energy levels for electrons in solids. The bands and gaps that the Schrödinger equation predicts. Without understanding the quantum nature of electrons in solids, there are no transistors. And without transistors, there is no digital world at all. The entire information age is a quantum technology that most people never think of as one. Then there is the laser, which is in your barcode scanners, your fiber optic internet cables, your eye surgery, your manufacturing, your rangefinders, and the little pointer the cat chases. The laser is Einstein's child because it works on a process he described back in 1917 called stimulated emission, where one photon of exactly the right energy passing an excited atom can coax that atom into dumping out a second photon perfectly in step with the first. Same color, same direction, marching in lockstep. Set up a chamber where this happens over and over in a cascade, and you get a beam of light where all the waves are perfectly aligned, which is what makes laser light so pure and so tightly focused, completely unlike the messy jumble of an ordinary bulb. It is the quantized energy levels of atoms, those rungs again, the same rungs Bohr found in hydrogen, that make the whole thing possible. There is more, and it goes deep into your life. The glowing screens and the bright efficient light bulbs that have taken over the world use light-emitting diodes, which give off light through electrons dropping down quantum energy steps in a semiconductor, releasing a photon of a specific color with each step. The medical scanner, called an MRI, the one that takes detailed pictures inside your body without cutting you open, works by manipulating the quantum spin of the protons inside your own atoms, flipping them with magnetic fields and radio waves, and listening to what they give back. The atomic clocks that keep the most precise time humanity has ever measured, accurate to a tiny fraction of a second over the entire age of the universe, work by counting the incredibly steady quantum vibrations of atoms jumping between energy levels. And those clocks are what make the satellite positioning in your phone possible, because finding your location depends on timing signals to within billionths of a second. Every time a map tells you where you are, a network of quantum clocks in orbit made that possible. Even the deepest workings of chemistry, the way molecules bond and react and build everything from medicines to plastics to the proteins in your body, is governed entirely by the quantum behavior of electrons. The strange, fuzzy rules from the glowing box are not off in some distant laboratory. They are running inside your phone, your body, your kitchen, and the sky over your head every second of every day. And then there's the technology that takes the very strangest parts of everything we have talked about, the superposition and the entanglement, the parts that drove Einstein up the wall, and tries to turn them into raw computing power. This is quantum computing, and it is the frontier right now, the thing that has companies and governments pouring billions of dollars into freezing tiny circuits down to near the coldest temperature possible and shielding them from the faintest disturbance. So let us walk through what it actually is, slowly, because the idea is gorgeous once it clicks, and almost everything you hear about it in the news is at least a little bit wrong. A regular computer, the one you are using, stores everything as bits, and a bit is just a switch that is either a 0 or a 1, off or on, nothing else. Every photo, every song, every word I am saying is just an enormous string of these zeros and ones, and the computer works by flipping them according to rules, unbelievably fast. A quantum computer replaces the bit with something called a qubit, a quantum bit which can be built out of something like the spin of a single particle or the state of a specially built tiny circuit. And here is the difference that changes everything. A qubit, being a quantum thing, does not have to be just 0 or just 1. It can be in a superposition of both at the same time, 0 and 1 layered together in a blend, the same way the electron went through both slits at once. One qubit holds a mix of both answers. Now, that on its own is interesting but not yet powerful. The power comes when you put many qubits together and entangle them, link them into a single shared quantum state, so that they are not independent little switches, but one big connected web of possibility. With ordinary bits, a string of, say, 300 bits can hold exactly one number at a time, one specific pattern of zeros and ones. But a string of 300 entangled qubits, all in superposition together, can hold a blend of an astronomically huge number of patterns all at once, more patterns than there are atoms in the observable universe, layered together in a single quantum state. The machine can then, in a sense, work on all of those possibilities at the same time, in parallel, rather than plodding through them one by one, the way a normal computer must. But here is the catch, and this is the part the breathless news stories always skip because it is the hard part. You cannot simply read all those answers out. Remember Born's rule. When you measure a quantum system, it collapses to just one result, picked at random, and all the other possibilities vanish. So, if you just build your superposition of a zillion answers and then look, you get one random answer, which is useless. The whole art of quantum computing, the genuinely deep and difficult part, is in cleverly arranging the calculation so that all those overlapping possibilities interfere with each other, like the waves in the double slit, in a way that makes the wrong answers cancel out and the right answer reinforce itself, so that when you finally do measure, the answer you want is overwhelmingly the one most likely to pop out. It is computing by orchestrating interference. You are conducting an orchestra of possibilities, so that they all crash together into the one note you were looking for. That is extraordinarily hard to do, and it only works at all for certain special kinds of problems where such a clever arrangement exists. And that is the other thing the hype gets wrong, because a quantum computer is not just a faster regular computer, and it will not be sitting on your desk playing your games anytime soon, if ever. For most everyday tasks, it offers no advantage at all. What it could be staggeringly good at is a small handful of very particular problems, and one of them is genuinely world-altering. Back in 1994, a mathematician named Peter Shor worked out a way that a big enough quantum computer could break the codes that protect almost all of modern digital security. The encryption that guards your bank account, your messages, and basically every secret transmitted across the internet. That security rests on the fact that ordinary computers find it hopelessly slow to break a very large number down into the two prime numbers multiplied to make it. A task that would take a regular computer longer than the age of the universe for a big enough number. Shor showed a quantum computer could do it quickly. Nobody has built a machine anywhere near big enough to actually do this yet, and it may be many years away, or it may turn out to be impossibly hard to scale up. But the mere possibility has governments scrambling to invent new codes that a quantum computer could not crack, a whole field racing to lock the doors before the key gets built. The other thing these machines could be wonderful at is far more hopeful, and it is the thing they may turn out to be truly best for, which is simulating nature itself. Because the world is quantum at its core, an ordinary computer is terrible at predicting how complicated molecules and materials behave, since it has to fake the quantum weirdness with brute force and quickly drowns. But a quantum computer is quantum, so it can mimic those molecules naturally, which could let us design new medicines, new materials, better batteries, and better fertilizers by simulating the quantum dance of electrons directly instead of guessing. That is the dream, anyway, a machine built out of superposition and entanglement. The two ideas Einstein found unbelievable, used to read the quantum book of nature in its own native language. And while the giant code-breaking machines are still far off, the spooky connection itself is already being put to work in another way, in quantum cryptography, which flips the strangeness into a shield instead of a weapon. Because of the rule that measuring a quantum system disturbs it, you can send a secret key encoded in quantum particles in such a way that any eavesdropper trying to listen in would unavoidably leave fingerprints, disturbing the particles and revealing their presence. So you can build a communication line where the laws of physics themselves guarantee you would know if anyone was spying. This is not a someday idea. It has been demonstrated over real distances, including, thanks to Anton Zeilinger and others, between ground stations and satellites passing overhead. The same entanglement Einstein dismissed as too spooky to be real is now being beamed down from space to keep secrets safe. There is also a genuinely mind-bending trick called quantum teleportation, which despite the name does not move any matter and cannot send anything faster than light, but does let you transfer the complete quantum state of one particle onto another distant particle, using a shared entangled pair and an ordinary message. effectively reconstructing the original state somewhere else while destroying it where it started. It sounds like pure science fiction, and it has been done in laboratories for years, and it may end up being the backbone of how future quantum machines talk to each other. I want to circle back now to something I rushed past earlier because it is one of the best stories in all of science, and it deserves to be told properly, slowly, the way a good story should be told late at night. It is the long-running argument between Albert Einstein and Niels Bohr, two of the greatest minds of their century, who liked and deeply respected each other, and who spent the better part of 2 decades trying to prove each other wrong about the nature of reality. It was never bitter. By all accounts, it was warm and even joyful, but it was relentless. And the place it played out most famously was at a series of gatherings called the Solvay Conferences, where the greatest physicists in the world would come together to argue it all out. The most famous of these was in 1927, and there is a photograph from it that has been called the most intelligent picture ever taken because of the 29 people in it. 17 either had won or would go on to win a Nobel Prize. Einstein is sitting right in the front row center. And it was at this gathering, with the new quantum theory freshly assembled and the randomness and the uncertainty laid out for all to see, that Einstein began his campaign against it. He could not accept a universe built on chance, and he set out to break the theory not by attacking the math, which he knew was sound, but by inventing clever thought experiments, little imaginary setups designed to show that the uncertainty principle could be beaten, that you could pin down more than the theory said you were allowed to, which would prove the theory was missing something. So the pattern at these conferences became something of a ritual. Over breakfast, Einstein would present a fiendishly clever thought experiment, some imaginary apparatus that seemed to let you measure two forbidden things at once and sneak past the uncertainty principle. Bohr would spend the whole day pacing and muttering and turning it over, often visibly troubled. And then by dinner, or by the next morning, Bohr would come back having found the flaw, the subtle thing Einstein had overlooked, and the uncertainty principle would survive once again. Einstein would not accept that particular defeat and then go off and build an even more devilish trap for the next round. He was not being stubborn for its own sake. He genuinely believed there was a deeper, saner layer underneath, and he was hunting for the one experiment that would force everyone to see it. The grandest of all these traps came at the next big conference in 1930, and it is so clever that it is worth walking through. Einstein imagined a box with a hole in its side, and the hole is covered by a shutter on a timer, and the box is full of light, and the whole box hangs from a spring scale so you can weigh it. Now, he said, you set the timer to flick the shutter open for the tiniest instant and let exactly one photon escape. And because the shutter was controlled by a clock, you know the precise moment the photon left. So far, you have nailed down the time perfectly, and here is the trap. Since the photon carries energy, and since energy has weight, by Einstein's own famous relationship between energy and mass, the box will be very slightly lighter after the photon leaves. So you just weigh the box before and after as carefully as you like, and the change in weight tells you the photon's exact energy. So now you would know both the exact time the photon left and its exact energy, both at once with no limit. And that combination is one of the forbidden pairs. The uncertainty principle says you can never have together. If Einstein was right, the whole theory would crack. The story goes that Bohr was rattled by this one, genuinely, that he spent an agonizing, sleepless night turning it over, unable to find the hole. And then, in the morning he had it, and the way he beat Einstein is the most beautiful part, because Bohr defeated Einstein using Einstein's own greatest discovery against him. Here is the flaw Bohr found. To weigh the box, you have to let it sit in gravity, and to read the new weight, the box has to shift its position ever so slightly as the spring stretches. But Einstein himself had shown in his theory of general relativity that a clock's ticking rate depends on its position in gravity, that time itself runs at different speeds, at different heights. So, the very act of weighing the box, of letting it move up or down in gravity to be measured, throws off the timing of the clock inside it by exactly the amount needed to blur the moment the photon left. Work through the numbers and the fuzziness in the time and the fuzziness in the energy, multiply back together to land precisely at the limit the uncertainty principle demands. Not a hair less, Einstein's own theory of gravity had enforced the very rule. He was using it to attack. Einstein conceded the point, but he was never truly convinced, not in his heart, and he stopped trying to prove the theory was wrong and shifted to a different claim, that the theory was not wrong, just incomplete, that it was missing the deeper layer. And that shift is exactly what led, 5 years later, to the EPR paper and the whole business of entanglement that we now know Bell and the experimenters eventually settled against him. Einstein went to his grave in 1955, still unconvinced, still sure that God does not play dice, still believing a sensible layer waited underneath. And the cruel and wonderful irony is that the questions he raised, precisely because he disliked the theory, turned out to be the most important questions anyone asked about it. The ones that led straight to the experiments that proved him wrong and opened the door to quantum computers. Even in losing, Einstein was more right about what mattered than almost anyone who was busy being correct. Now, I have to stop and bust a myth, because if you have heard anything about quantum mechanics floating around out there, you have probably heard some version of the idea that consciousness creates reality, that the universe needs a conscious mind to look at it before things become real, that your awareness is what collapses the wave function and brings the world into being. You will find this idea all over the place, in self-help books and documentaries, and 1,000 confident posts online, and it sounds like it follows from everything we have talked about, from the observer in the double slit, from the cat in the box. And I want to be careful and honest with you here, because this is the spot where the science gets twisted the most. The truthful answer is that the word observer in quantum mechanics does not mean a conscious person, and it never did. An observer in the physics is just any interaction with the wider environment that records information about the system, any measuring device, any stray particle, any bump that entangles the quantum thing with its surroundings, exactly the decoherence we talked about earlier. A photographic plate observes, a clump of air molecules observes, a speck of dust observes. None of these has a mind, none of them is aware of anything, and they collapse or decohere the wave function just fine. The experiments work exactly the same, whether a human is watching the screen or whether the whole thing runs in a sealed room with the results saved to a hard drive for you to check next week. Your mind has nothing to do with it. The witch path detector in the double slit does not need a person reading it. It just needs to make a record. So, while it is true that there are serious, careful thinkers who have wondered about the role of the mind at the very deepest level, and while the measurement problem is genuinely unsolved, the popular idea that your consciousness reaches out and conjures reality into existence is not what the physics says, and you should be gently suspicious of anyone selling it to you. The universe was busy collapsing wave functions for billions of years before there was anyone around to watch. The strangeness is real, but it is not about you. Here is one more piece before we wind down, and it is a newer and more speculative area, so I will flag it clearly as a place where the science is still being worked out and you should hold it a little loosely. But it is too wonderful to leave out. For a long time, people assumed that all this delicate quantum behavior could only survive in carefully shielded laboratories, frozen and isolated, and that warm, wet, messy, living things would scramble it instantly through decoherence, so that biology and quantum weirdness lived in separate worlds. But over the last couple of decades, evidence has been building that life may actually be using quantum tricks right out in the warm and the wet in ways that are genuinely surprising. And the young field studying this is called quantum biology. The best example, and the one with the strongest evidence behind it, is how some birds find their way during migration across thousands of miles with no map. There is a leading idea, supported by a growing pile of experiments, though not yet fully nailed down, that certain birds can sense the Earth's magnetic field using a quantum effect happening inside special molecules in their eyes. The thinking is that incoming light creates a pair of electrons with entangled, linked spins, and the way those linked spins evolve is nudged ever so slightly by the direction of the Earth's magnetic field, which changes the chemistry in a way the bird can somehow perceive, effectively letting the bird see the magnetic field as a kind of visual signal laid over the world. If this holds up and the evidence keeps leaning that way, then a robin crossing a continent is running a live quantum experiment inside its own eyeball, navigating by entanglement. The same spooky phenomenon Einstein could not stomach. There are other tempting hints too, though several are more contested, and you should treat them as open questions rather than settled facts. There is evidence that the first step of photosynthesis, the way plants and certain bacteria capture sunlight and shuttle that energy to where it is needed, may use a kind of quantum effect to find the most efficient path almost instantly, the energy exploring many routes at once, the way the electron explores both slits. Though researchers still argue about how big a role this really plays in a warm leaf. There are even speculative ideas, far more shaky and not widely accepted, that quantum tunneling might play a part in how our sense of smell works, or in how mutations occasionally happen in DNA when a single proton tunnels to the wrong spot. I want to be clear that the further down this list you go, the thinner and more debated the evidence gets, and a responsible person holds most of it loosely. But the headline is genuinely remarkable and increasingly hard to dismiss, which is that the strange quantum rules are not locked away in cold laboratories after all. They may be woven into the machinery of life itself, running inside leaves and eyes, and maybe even inside you, keeping the whole living world turning without ever once announcing themselves. I told you earlier that big things look normal because they get tangled up with their surroundings so fast that the quantum strangeness gets buried instantly. That is true, but I left out something wonderful, because there are special situations where you can keep a large number of particles so cold and so isolated and so perfectly in step that the quantum behavior does not get buried, and instead it grows until it becomes big enough to see with your own eyes. These are called macroscopic quantum states, and they are some of the most beautiful things in all of physics, because they are the quantum world breaking out of the world of the invisibly small and showing itself at human scale. The clearest example goes all the way back to Einstein again, and to a physicist from India named Satyendra Nath Bose. In 1924, Bose worked out a new way of counting how particles of light share out among themselves, and he sent his paper to Einstein, who saw immediately that it was important, translated it into German himself, and got it published. Then Einstein took the idea further and predicted something strange. He calculated that if you took a gas of certain kinds of atoms and cooled it down to almost the coldest temperature possible, very near absolute zero, the point where all motion nearly stops, then something dramatic would happen. The atoms would stop being separate individuals and would all collapse together into the exact same single quantum state, all of them sharing one wave function, all marching in perfect lockstep, behaving not like a crowd of separate atoms, but like one giant atom smeared across the whole sample. This predicted new form of matter came to be called a Bose-Einstein condensate, and it is sometimes called the fifth state of matter, after the familiar solid, liquid, gas, and the plasma you find in stars. Einstein predicted this in 1924, but actually making one turned out to be brutally hard, because you have to cool atoms to within a hair of absolute zero, the billionths of a degree above the coldest temperature that can exist, colder than anything in nature, colder than the depths of empty space. It took 71 years. Finally, in 1995, in a lab in Boulder, Colorado, two physicists named Eric Cornell and Carl Wieman used lasers and magnetic traps to chill a tiny cloud of about 2,000 rubidium atoms down to that unthinkable cold. And the atoms did exactly what Einstein had said they would, collapsing into a single shared quantum state, one little blob of matter, all behaving as one. A physicist named Wolfgang Ketterle made one with sodium atoms a few months later, and the three of them shared the Nobel Prize for it in 2001. The Nobel Committee described what happens by saying the atoms sing in unison, which I think is a lovely way to put it. They had taken Einstein's 70-year-old prediction and held the quantum world in their hands, big enough to photograph. And there are other macroscopic quantum effects that you have actually benefited from. There is superconductivity, where certain materials cooled down far enough suddenly lose all electrical resistance, so that an electric current can flow through them forever, around and around a loop, without losing any energy at all, which only happens because the electrons pair up and drop into a shared quantum state together. The enormous magnets inside the medical MRI scanners are superconducting, which is the only way to make magnets that strong. So the next time you hear about someone getting one of those scans, that is a large-scale quantum effect doing the heavy lifting. And there is superfluidity, where a liquid cool enough loses all its thickness and friction and starts doing genuinely bizarre things, like flowing uphill on its own and creeping up and over the walls of its container to escape, because the whole liquid is moving as one quantum thing with nothing to slow it down. These are not subtle laboratory curiosities you need delicate instruments to detect. They are the quantum world made large enough to watch a liquid climb out of a cup. Before we get to the deepest unsolved problem, I have to come back one last time to the double slit, because there is a version of it so strange that when I first read about it, I had to put my phone down and stare at the wall for a while. And it is a genuine experiment that has been done, not a thought experiment. It is called the delayed choice quantum eraser, and it pokes at the very weirdest part of the measurement business, which is the question of timing, of when exactly the particle decides what it is going to be. Remember the rule from the double slit. If you have which path information, if the universe knows which slit the particle went through, you get particles and two blobs and no interference. If that information does not exist anywhere, you get the wave and the interference stripes. Now, here is the twist that the eraser adds. Physicists worked out setups where a particle goes through the slits and the record of which path it took gets created. But then, crucially, you arrange things so that you can choose later, after the particle has already hit the screen, whether to keep that which path record or to scramble it, to erase it, so that the information is destroyed and can never be recovered by anyone. The choice to erase or keep happens after the particle has already landed, and the result is the part that makes your head spin. When you look back at the particles for which the path information was erased, they show the interference pattern, the wave behavior, as if they had gone through both slits, and the particles for which the path information was kept show no interference, the particle behavior, as if they had picked one slit, even though, in both cases, the particle had already hit the screen and was long gone before the choice to keep or erase was made. It looks, on the face of it, as if your choice in the present reached back into the past and changed what the particle had already done, as if the future decided the past. Now I have to be careful and honest here, because this is exactly the kind of result that gets wildly oversold, and you will find people insisting it proves you can change the past or send messages backward in time, and that is not what it shows. The careful truth is more subtle and, I think, even stranger for being so slippery. You cannot actually see the interference pattern in the raw data on the screen at all. It only appears when you go back afterward and sort the particle landings into groups based on the matching information from the erased or kept records. And you can only do that sorting after both pieces of information are brought together, which always happens at ordinary speed in the normal forward direction of time. So no message travels backward, and you cannot change anything that has happened. But what it does show, beyond any doubt, is that the simple story where the particle definitely went through one slit, or definitely went through both, as a settled fact at the moment it passed the slits, is just wrong. The particle does not carry a secret answer about what it did. The pattern that emerges depends on information that did not even exist yet when the particle was in flight. The past in the quantum world is not as fixed and finished as you would like it to be, and that is about as far as I can take you into that particular rabbit hole without falling all the way down it. So we have come a very long way from a glowing hot poker to entangled photons beamed down from satellites. And you might think that after 100 years and all this success, the story is basically finished, that physics has the world figured out. It does not, and I would be lying to you if I let you walk away thinking it did. There is a crack running right through the foundation of physics, a deep and embarrassing one, and it is the great unfinished business of the whole subject. So let us end the science part of our journey by looking honestly at the thing we still cannot do. We have two magnificent theories of how the universe works. One of them is quantum mechanics, everything we have been talking about, which rules the world of the very small, the particles and the atoms and the fields, with that staggering decimal perfect precision. The other is Einstein's general relativity, his theory of gravity, which describes gravity not as a force, but as the bending and curving of space and time itself by anything that has mass, and which rules the world of the very large, the planets and the stars and the galaxies and the whole shape of the cosmos. Both theories have passed every test anyone has ever thrown at them. Both are, as far as we can tell, correct. The problem is that they flatly contradict each other, and when you try to make them work together, the math falls apart completely, spitting out nonsense and infinities, refusing to give any sensible answer at all. For the most part, this does not matter in daily practice, because the two theories rule separate kingdoms that rarely overlap. Gravity is so unbelievably weak compared to the other forces that it is utterly irrelevant for a single tiny particle. So when you are doing quantum mechanics, you can just ignore gravity entirely. And the quantum graininess of the world is far too fine to matter for a planet or a star. So when you are doing gravity, you can ignore the quantum stuff. Each theory works beautifully in its own domain, and the domains almost never touch. Almost. There are two places in the universe where something is both extremely massive, so gravity matters enormously, and extremely tiny, so the quantum rules matter enormously, both at once. And in those two places, our physics simply stops working. One is the very center of a black hole, where an entire dead star is crushed down into a point of essentially no size at all. The other is the very beginning of everything, the first unimaginable instant of the Big Bang, when the whole universe was squeezed into something smaller than a particle. In those two situations, you need quantum mechanics and gravity to speak to each other at the same time, and they cannot. And so, at the heart of every black hole and at the birth of the cosmos, there is a question mark, a place where our finest theories throw up their hands and admit they do not know. The dream, the great unfinished quest that some of the brightest people alive have spent their entire careers chasing, is a single theory that would join the two, a theory of quantum gravity that would describe gravity itself in the chunky, probabilistic quantum language, and finally let the rules of the very small and the very large sit at the same table. There are candidate ideas with names you may have heard, like string theory, which imagines that the most basic things are not points at all, but tiny vibrating strings, and loop quantum gravity, which suggests that space and time themselves come in tiny, indivisible chunks, that even emptiness has the smallest possible grain, the way energy did in Planck's box. These are serious, beautiful, deeply worked out ideas, and not one of them has yet made a clean prediction we have been able to test, because the situations where they would differ from ordinary physics are so extreme, so far beyond anything we can build or reach, that we have no way yet to check them. So the crack remains open. 100 years after Planck reluctantly chopped energy into pieces, we have built the most accurate description of nature in human history, and we still do not know how its two halves fit together. The story is not over. It may be that the strangest chapter has not even been written yet. So there it is, as much of it as I could fit into one long sitting, the whole strange 100-year journey from a man who did not believe his own answer about a glowing box, through a patent clerk who insisted light came in chunks, through a prince who said matter was a wave, and an Austrian who wrote the wave down, and a German who found the limit on what can be known, through a cat that is both alive and dead, and a debate between two friends that lasted decades, all the way to entangled particles that hold hands across the galaxy, and machines we are building right now to compute with the very weirdness that drove Einstein to distraction. And the thing I keep coming back to, the thing I find so astonishing every time I read about it, is that none of this is a story about some faraway, exotic place that has nothing to do with you. It is the story of the floor holding you up, and the sun warming the sky, and the screen glowing in front of you, and the atoms that make up your own hands. Every one of them running on rules that say a thing can be in two places at once, that the universe rolls genuine dice, and that reality stays soft and undecided until the moment the world reaches out and pins it down. Einstein spent his life refusing to believe the universe could really work this way. And Einstein was wrong. And somehow that is the most comforting part of the whole thing to me, because it means that even the greatest mind of the age looked at the truth and found it too strange to swallow, and the truth just sat there, patient, being strange, waiting 100 years for us to catch up to it. We still have not fully caught up. There is a crack in the foundation, a cat still waiting in its box, an argument about what any of it means that has never been settled and may never be. But the world keeps right on humming along underneath us, fuzzy and probabilistic and entangled and impossible, holding up the chair and lighting up the sky, completely unbothered by the fact that the cleverest creatures it ever produced still cannot agree on what it is doing. And on that note, I think it is a good place to stop. Thank you for staying with me through all of it. Take care of yourself, and I will see you in the next one.